Welcome back to AstroAssembly, and kicking off our first speaker for this afternoon is Mastrangelo.
All right, well, I appreciate it, Scott. Thank you to Michael as well. And then we also have Rick giving me some of the tools I'm using today. So appreciate all of you having me here today. First time learning about skyscrapers was a few months ago, and Michael was telling me about the organization and what you all do. And I didn't know this was such a big event. When I pulled onto the road, I was like, wow, this is actually be a pretty good crowd. So I'm excited, and I'm glad it's kind of like a meeting of the minds, seeing everyone here together. And yeah, we're going to learn about the sky sciences. Of course, I'm a meteorologist. It's not me. I work with meteors. I talk about the weather, and that's exactly kind of my realm. So once I get into astronomy, which you'll learn, I also have to talk about quite a bit too. I'm a little bit out of my realm. So while I am a scientist at heart, I don't know quite as much about astronomy that I do meteorology. So let's get right into it. I'm meteorologist Mastrangelo, and of course, I'm glad to be here. I'm part of Storm Team 10, so I work at Channel 10 WJAR, and we are based out of Cranston, Rhode Island, just right off Route 37, so not too far from here. I live in Providence, Rhode Island with my girlfriend, so not too far of a drive from where we're at right now. And yeah, I'm actually fairly new to the area, so I'll kind of talk a little bit about myself before I get into the deep dive about meteorology and astronomy, of course. So yes, I've been working as a meteorologist now since 2022. I previously worked in Erie, Pennsylvania, which I don't know if anyone knows where that is. There's some claps there. Yeah. It's a fairly small community. It's about 150,000 people total within that just general area. So a little bit smaller, actually quite a bit smaller than our cities here. And of course, our metro area, which we call the Providence metro area. So I'm a New England native. I actually grew up in northern Massachusetts, in Groton, Mass. So that's actually probably about, I'm like the chairs, it's about an hour 15 from where we're at right now. So kind of the localities of Rhode Island and Rhode Island weather, alongside all the community notes that I've kind of learned here within the past 2 years. It's all brand new for me. So I actually had a cool segment this summer. It's called Summer of Fun, where I was literally just going to all different Rhode Island attractions, learning some of the quirky things, some of the cool things, and meeting some great people along the way as well. I've always been interested in the weather. I feel like that kind of goes hand in hand with astronomy. A lot of folks that love the stars and, of course, love the planets, they've been doing that since a young age. I've been actually telling the weather, believe it or not, over the intercom since elementary school. I kind of took a little bit of a hiatus in middle school and high school when I was in puberty, trying to be a little bit cooler and everything like that. But it's always been kind of a career path of mine to be a meteorologist. You guys know how it goes. Difficult math, Calc 1 through 3, differential equations, physics 1 and 2, calc-based, and then an earth science curriculum. That was kind of my forte. I wouldn't say the grades were my forte in physics and math, but I did really appreciate the science and, of course, all the ideology that goes along with meteorology. So back in 2022, I graduated from Penn State with a Bachelor of Science in Meteorology and Atmospheric Science. So not too long ago, you can see some photos here. These are actually both from the past year, where I was on Block Island filming a segment for that Summer of Fun thing. You can see I'm up in a tree doing some fun stuff there. Also cooking in the middle of our newsroom. Only something we can do on the weekend, because when everyone's there, yeah, especially if you're a vegetarian, you don't like to smell the bacon that's going on in the news there. So we like to have fun with what we do. Everyone thinks the news is so serious, and yes, it's very, very serious when we have a big storm brewing or something like that. We also like to enjoy ourselves. We're just normal people as well. So that's a little bit about myself. I would say not a whole lot to add aside from that. So I joined WJAR in May of last year, so 2024. I've only been here for about a year and a few months. I'm the weekend morning meteorologist, so that means Monday through Friday. I'm essentially useless. Not kidding. I actually do make some weekday morning appearances, and of course, a lot of fill-in work that kind of goes with this gig too, because someone's off, got to be filling in for their position. So in terms of our team, you may have seen him before. Mark Searles has been in the market for forever now, over 25 years. Christina Ernie, she's our morning meteorologist. Jason Doris is our midday meteorologist, our noon meteorologist. Nick Russo, also a newcomer alongside myself last spring. He's the weekend evening. So I'm the weekend morning, he's the evening. And then, of course, I'm the last one here, the youngest one on the totem pole by a few years. So it's a great team. I've only been, of course, working them for a year and a half now, but I've learned a lot of great things. Jason and I, he's the midday meteorologist. When I come in during the week, we are just nerding out 24/7, just talking, blabbing about sports and blabbing about weather. for the most part. So what is my routine? It's an early wake up being a morning meteorologist. During the week when I'm filling in for Christina, I get up at 2:30. I have to be in at 3 a.m. On the weekend, a little bit different story, 3:30, if that sounds any better to anyone. But I've been up since that time frame this morning. And of course, so what I do as I get in, I see what's going on. And on my drive in, I'm taking note of what's going on. If there's fog, of course, hope I had that in my forecast the night prior. But you're just kind of, first thing you're doing when you're heading into the studio, you're analyzing what's going on, your current conditions. After that, you can start getting an idea of creating a forecast for what that day is going to look like. Is the fog going to break? Are temperatures going to climb on up? What are kind of some factors that are going to be inputted into this forecast? A lot of our job, as much as I love to get technical all the time, updating social media, updating the web, a lot of media and content creation, unfortunately, does take quite a bit of my time during the day. So I'm doing that stuff a lot. It's important to get that information out on the air alongside to our social media so people can really get a better understanding of what to expect. And then after that, I'm heading on air. And just as simple as it goes, past, present, future. As I was talking about, observations are the first thing we look at as meteorologists, and kind of what has already transpired has led us to that point. And then, of course, we focus on the future, and that's why we get paid the big bucks to be wrong. All right, so the study of meteors, right? No, I'm sure all of you actually know this, which is something of a first for my first groups I've been talking to before. So yeah, meteorology in general, it's the field of science dealing with the atmosphere and its events, including both weather and climate. Now, people think weather and climate are the same thing. Weather is current, climate is past and in the future, just a long-term version of kind of what weather is. It's a current, weather is current, climate is essentially a long duration of kind of how that weather has acted and how it stacks up with previous events and kind of previous, I would say, data sets or normals. So of course, the four earth sciences: astronomy, how Earth relates to space and time; meteorology, the atmosphere; oceanography, how marine ecosystems interact with the oceans. Don't have to deal with that a whole lot. And of course, geology, we become the experts on that as well. So there's an earthquake. Of course, we had the tsunami warning earlier this summer. We were the people were turning to, like, oh, we're going to get a tsunami in our region? No, we're not going to get a tsunami in our region. It's another ocean it's coming from. But we're kind of that backbone scientist that the station essentially relies on to give you that information. So let's talk about layers of the atmosphere. Of course, you look up, you don't see a whole lot, but there's plenty of things going on. Our atmosphere, well, you got to think about it as a gas or more as a fluid. It's being held down by Earth's gravity. So it's being kind of pulled to Earth's surface. If it was not, we didn't have any gravity, then we'd have no atmosphere. We wouldn't be here today. There'd be no life in general. So the chemical composition, density, temperature, all these things change within each layer of the atmosphere. What I have right here is this is known as a temperature profile. On the right, this is height in miles. On the left is our height in kilometers. This line in the middle right here, this is a line of temperature. And as you can see, it's not completely linear. What we see here is temperatures kind of go up and down throughout different parts of the atmosphere. This really does not impact us unless it happens on the bottom here, which is the troposphere, kind of where we see the majority of weather happen. Good news about the atmosphere, it protects us from a lot of things. Talking about UV radiation, of course, meteors burning up, things like that. And of course, it gives us the air that we can breathe. So the atmosphere is very, very important. That's why monitoring it is crucial, especially in today's day and age. So what drives the weather? Well, think about it. It's pretty much the sun. Not only the source for life, it's also the source for weather. The reason why that is different heat fluxes. Radiation that comes from the sun, it heats things like water, even plants. Evapotranspiration is a big part of kind of what drives cloud cover to develop and what moves our weather patterns across what we see as west to east. That's more kind of dictated by the spin of Earth. So it does involve somewhat of meteorology and astronomy coming together to get these things all together. Oceans, topography, and of course, motion in space also driving factors for what causes the weather in general. Topography, very, very important. Of course, you get a lot of moisture. That meets a mountain range. That moisture is lifted, and then you get a cloud forming. So typically you can see this more on the west coast of the United States. If you've ever seen like a cap cloud on Mount Rainier or some of those large stratovolcanoes there, that's due to topography. And we see that on a broad scale on many actually events that we see even here locally. So it's not always as distinct as that, but topography plays a big, big factor in friction alongside uplift that creates clouds for our atmosphere. In most cases, Earth's atmosphere acts like a fluid. If you've ever kind of studied satellite imagery before, you take a look how the clouds are moving. They're not moving like, they're essentially like water flowing. It's almost like a waterfall. If you watch a cyclone spin, all of that movement of air and cloud is essentially treated the same with a fluid. And that's also very important when we're studying these things, because you can apply certain laws, such as Newton's laws, to some of the things we talk about. So let's talk about what level the clouds hang out. Troposphere. So that was the lowest part of that profile that I showed of our entire atmosphere. You can essentially see it from 40,000 feet. Sorry, it's a little bit difficult to read up there, all the way down to the surface level. There's several different types of clouds as well. Cirrocumulus, those are some of the high clouds that kind of look a little bit dotty. Some also call them kind of fish scale type clouds. Or sorry, no, those are actually altocumulus. The cirrocumulus have a little bit more of a wispier look to them. They're actually made of ice crystals, because we learned that the higher up you go in our lower part of the atmosphere, the colder it gets. So all these clouds that are certainly, for the most part, above, I would say, roughly 6,000, 8,000 feet, do typically have some sort of ice crystal, especially through the parts of the winter time into the mid-winter there. So let's talk about what we have in terms of the troposphere. Well, it's very unstable. There's a lot of heat interactions and a lot of heat exchange that creates chaos. And essentially that chaos is what we're forecasting each and every day. The tropopause, well, that's the top of this layer. And as you can see here, this is a cumulonimbus cloud. So the very basic cloud to talk about is a cumulus cloud. Those puffy clouds, they kind of look like a marshmallow. You see them on fair weather days. You also see them on some of the most active severe weather days as well. The bad news is when these cumulus clouds start rising and they become cumulonimbus clouds, and they rise so high in our atmosphere, and they're essentially the same thing. You can think about it like an atomic bomb, essentially, where we're seeing uprising air. But once we reach the end of the troposphere, which I told you the lowest level of the atmosphere, we see something happen. Stability takes over because the stratosphere is a lot stabler. So the cloud can't find a conducive environment to keep itself going upward, and it actually spreads out, creating an anvil. So the same thing you would see in kind of a video, like one of those vintage videos of a large bomb going off, where you see that anvil on the top. So we have a little bit of an idea now of where kind of the layer is of these clouds we're talking about. And it gets a little bit more difficult to differentiate these clouds when you're talking about modeling and when you're talking about forecasting, because all these different clouds, they have different kind of density. They have a different way of kind of how you can see through them. Like you can see through a cirrus deck when you're observing the sky pretty easily. But if you have a low-level stratus deck, that thing is very, very thick, and you're not going to be able to see through and actually gaze at stars. All right, so we'll get a little bit closer here to what we're exactly talking about, and it's going to be cloud forecasting, because what better way to kind of know whether or not you're able to see the stars, see the moon, observe distant galaxies, than actually knowing if there's going to be clouds in the sky. Now, tonight, I'll give you it. It's a pretty good forecast. You don't have to do all of this or go through all this, and I'll kind of explain, too, there's different scenarios of when you can kind of have more forecast confidence and don't need to look at a whole lot of things, opposed to other times where it's a little bit more difficult. Where it gets really difficult is when we have several cloud layers, because that means you can't really differentiate that from the top when you're looking down. And when you're looking up too, you can only really differentiate that from the bottom with some of the sensors we have here on the Earth. It's the in-between where it gets a little bit more difficult. So in terms of the steps, first thing we do for cloud forecasting, data analysis, as I was talking about when we come into the studio each and every morning. I mean, we're pretty much doing the same thing. The model initialization, too, is our secondary step. So what you need to find is the model actually lining up with what's going on. If that's not happening, you got some major issues. Third thing, model interpretation. That's essentially determining what the model is outputting. Is that actually going to be the case? Are these models lined up to a place where we can actually have a good idea of what's going to be going on? Number 4, a little bit of an optional deep dive. As I was talking about, some situations are a little bit more complex than others. So taking that deep dive can definitely pay dividends if you are forecasting a difficult situation. And then the final thing you do is you create a forecast And of course, that's the last thing we do before we go on the air. So you might notice my voice is a little bit hoarse. I'm not sick. I was at the Penn State whiteout last weekend. I was, they're screaming at James Franklin, the Penn State Nittany Lions. So that's why I do apologize. My voice is a little hoarse. Let's talk about the first thing we're talking about, data analysis. We head into the studio. Let's say we're heading to the beach. We see this right now. There's a few layers of clouds. One of the things we're going to look at is what exactly is going on in terms of these clouds. Where are they moving? Are they kind of lessening in coverage? Are they increasing in coverage? The thing you want to look at is METAR observations. And these are put out every single 5 minutes at certain sites, at least every 30 minutes at every METAR site. And these are state airports. And all of this data is being fed to the National Weather Service. So it's free and it's public. And it's very, very crucial for our jobs and very crucial for other gigs too. So looking at current METAR observations, that is your current conditions that we're talking about. Webcams as well. Best friend, especially when we have no idea what's kind of going on in the coastline. Not every single town has a METAR station. So what are you going to do? You're going to look at webcams. We look down to Galilee all the time, Newport, as well as New Bedford, to see if there's a little bit of some fog in those locations. Your webcams really help you out to kind of make sure that what you're seeing in terms of the observations is actually what's going on in real time. Satellite data, that gives you the most comprehensive overview, but as we know, there are some limitations to that as well. So let's first talk about these METARs. I would say if anyone wants to, this is the link you want. It's the weather.gov link. And if you click in this link, I'm sure we'll hopefully be able to share this presentation after this. Either way, I can send out some links that might be helpful for everyone. You put in that link and you put in any airport code and you're getting weather data every 5 minutes. I have this bookmarked for every single station we have in Rhode Island and Southeast Massachusetts. And the big two things we look at in terms of cloud cover are the first two things, which are, of course, two different areas we look. I'll use this actually laser pointer here, see if I can get that going. Don't blind myself. This area right here is the first column of what you find at this website. First thing is the temperature. The second thing is the dew point. Temperature and dew point are very different. When they come together, that means that the air is fully saturated. When you get fully saturated air, you get fog, you're essentially in a cloud. Something we were talking about Washington, the entire summer, they are essentially fully saturated. And that's why it's actually very difficult to see a lot of clear days on top of Mount Washington in the summertime. So you head to this area, you see that these temperatures are a little bit different. It's good news in terms of cloud cover at the ground level, but we do know that that dew point could be a little bit closer to the air temperature higher up in the sky. So it does mean that there could be some clouds somewhere. And we actually are seeing that in this secondary column here. There's 3 different levels that we're seeing these, or 3 different sky conditions we are seeing here for this third area. The bottom one here is clear. The secondary one is few. And the third one is scattered. You talk about when we're on air, we don't really use those terms, but these are the official METAR definitions. So us as meteorologists, we kind of translate that into a little bit of layman's terms. So as we can see here, clear is essentially clear or sunny, and that means 0 to 1/8 of the sky is covered by cloud cover. And you're like, well, how do you know that? Well, there's actually a sensor. It's called a ceilometer, and what it essentially does is it sends a beam up in the sky at all 8s of the sky to determine what the coverage of the sky is. If it gets a return, of course, that means that energy is being returned back to the signal and there's a cloud there. So essentially what this few means is at least 1 to 2 of those beams did hit a cloud and return less energy to what was being shot up into the sky. So this is beneficial information to kind of know. Let's say it's 10:20 at night tonight. We see that few there. We know that perhaps 1 or 2/8 of the sky is being covered. Now, us meteorologists on TV, we use different terms because it's a little bit easier to understand. It's a bit of a pain in the butt because there is some overlap, such as partly cloudy, partly sunny, essentially the same thing. If you hear someone say partly sunny and partly cloudy, there's not much change to be had. So now you know that. Mostly cloudy, a little bit different story. Mostly sunny, we know that's greater than half for either side of the spectrum, more clouds or more sunshine, overcast, completely cloudy, and of course clear. That means you are good to go in terms of seeing any stars, hopefully no full moon to drown out your light. So what I've also included here is another depiction of what a station model looks like. So I was talking about all these METAR sites and how they put out different data. This is what a raw METAR looks like. So for example, right here, what we're seeing in the Providence area, which is actually TF Green Airport, is more of a southwest wind. You can see that wind barb is pointing to the north and east. That means the wind's coming from the south and west. And you can also make out what up there is our temperature and dew point. So a little bit difficult to see. Nonetheless, it's very important to see those dew points are 2 degrees below our air temperature. So that means we're not far away from having some clouds potentially on the ground level. But what we do see, and actually you don't see any other instances of this, is clear skies. All of these sensors are reporting clear skies. That little circle you see in the middle, how it looks a little bit like an eclipse, that essentially fills in like these 1 to 2/8 to show what percent of the sky is being covered by clouds. So you can essentially look at this map and see that we're seeing clear skies pretty much through the majority of the region, potentially some fog down there in Montauk, New York, as well as, I don't know exactly where that is, Marshfield, Plymouth area, likely a little bit of some fog there too. So that's how you look for METARs. It's just kind of a more difficult and intuitive way to look at what the current conditions are. And if you want some more information pertaining to this, I think this is kind of how Michael found me in the first place. I do a Sunday Science topic on this. And you can actually search sky coverage Rhode Island. You'll probably find this video pretty swiftly on YouTube to get a little bit more information pertaining to that. All right, so now we know what's going on. Now we got to figure out what's going to happen. And that's exactly what we do. But there are a few more steps we need to take. And one of the things I do when I come in every single morning is take a look at the satellite. Now, the big issue with satellite, at least visible satellite, which is the most useful satellite, you can't see it during the nighttime. It needs the sun's light to actually reflect off Earth for you to be able to see what's going on that satellite. So at night, we use this product called the microphysics product. And essentially what that does is through a series of calculations, the model or the satellite, and of course, the only reason this is sensible is because of the heat these clouds put off. If these clouds have the same temperature as the ground, they essentially show up as nothing. It's all about the measure of radiation that's being emitted from these clouds. And due to those numbers, this microphysics product can actually differentiate what these different clouds are. So as we can see right here, some of these sevens, we look down the list, some high thin clouds. So that wouldn't be causing any issues, of course, if we're observing the sky. But we look too far to the west, and there are some thicker clouds, some 5s and 6s. So what that means essentially is those are a little bit of some thicker clouds and maybe just a touch lower elevation. Overall, clouds are a little bit thicker when you head down to the ground level. So it's very important to use this microphysics product for us when we come into the studio so we know what type of clouds we're dealing with before the sun comes up. Because if the sun comes up and we don't know what type of clouds we're dealing with, it could be a completely different forecast than what we were thinking. So the sun comes up. Nice. We can see the visible satellite. And this is actually just from a few days ago. I obviously overlaid this with Massachusetts, kind of split down the middle. What you see with visible satellite product is essentially exactly what is going on. So one of the things we use it for is wildfire detection. If there's anything big going on in the sky, of course, we can see these things. You can even see the northern lights when we do get that at night. Of course, that's a visible product, but the whole ground is black because you can't see any of that illuminated ground. So what happened in the past and what's going to happen now, that's what we're talking about in terms of all this data analysis. The satellite data, the critical tool, microphysics at night. The best tool during the day, of course, is that visible satellite, so you know exactly what's going on. Like, for example, this right here is a cirrus deck. You can see how these clouds are a little bit more wispier than what we're seeing down here. This is a cumulus deck of clouds, and we can just kind of tell that these clouds are, yes, a little bit more separated, but they're a little bit thicker. They appear more of a puffy white opposed to that, I would say, semi-transparent white that you see with more of those cirrus clouds. So Where this gets tricky is around sunset and sunrise. It's kind of when we do have just odd lighting overall in terms of the satellites. So all of this data, I would say, for the visible and the microphysics gets a little bit wonky. That's kind of more of a time where you kind of want to rely on what's going on in terms of just those observations, what you can see and what you can make out, especially if the sun's coming up and outside gives you the best idea. All right, so number 2 comes model initialization. I'll show you how to get to the models in just a little bit, but let's kind of focus on how we start in terms of the models. So we were just looking at that satellite, right? Well, how does that line up to our model? And that's a very important question we ask each and every morning, not just for clouds, also for precipitation, also for temperatures, pretty much any attribute of the weather forecast. We need to make sure that is lining up with what we're seeing on the models. And it's not just one model, too. You like to see that amongst many different models that you are potentially using. Not saying you have to use different ones in the first place. But for example, this is the 18Z satellite. Z is Zulu time. That's what us meteorologists have to use. Of course, that changes depending on the time of year, how many hours back that is set from Zulu time itself. But as we can see here, look up the Hudson River Valley through New Jersey, even to parts of central New Hampshire and Vermont. That's lining up pretty well with what we're seeing here on the Earth. So that would be some decent model initialization. However, these high-think cirrus clouds are very prominent there. You look out towards Erie, Pennsylvania, for example. It appears there's a lot more clouds showing up on the model, especially west of Erie, than what we're actually seeing in person. So, for example, the HER would be doing a decent job at projecting what's going on for our region here in New England, at least Western New England, but not as great of a job here through the Erie area. So a comparison of satellite and radar to the first frames of any model is crucial to make sure your data is good and that you should keep on using it in the first place. Of course, models that match current conditions will tend to perform better overall as you head into the future. So where to find models? There's a few areas you can find on the internet that I would say have paywalls and make seem like great sites to use. These are the 2 I use, actually, in operational forecasting. Pivotal Weather alongside Tropical Tidbits. You may have heard of either of those 2. They're both very well known, very user-friendly. It's a lot of information to digest, so of course it takes some time to get used to. So that's very useful for finding cloud modeling, which is essentially a step forward than what you have for my forecast. I wouldn't say my forecast because I put a lot of effort in my forecast, but at least the National Weather Service forecast or your Weather Channel app. If you want to look at what actually may be going on exactly and have a better idea about it, you can use these 2 tools and look at different modeling to kind of give you a better perspective of what the cloud projections may be looking like further on the day. You want to find that initialization, though. And of course, the satellite data we were talking about as well. 2 very good areas. College of DuPage Meteorology has some great resources. I use them for severe weather as well. And then the Ghost East imagery is very, very good. The Ghost 19 puts out some very nice photos. You can also tune into our broadcast. We'll let you know what exactly is going on for that night. At least we'll try our best to have a correct forecast for you. All right, so we're on to step 3 in terms of forecasting the clouds, interpreting the model. So exactly what is the modeling showing? Is it outputting something different than expected? Of course, we know if it's not lined up from the beginning, then it's not really too useful. You want to find something that may have some initialization. If none of them do, then the closest thing might be your best bet. It also may not be. It's weather. It's predictive science. It's never perfect, and that's why we feel like we're kind of always learning, always growing, and getting better at what we do. And as a young meteorologist, that's something I need to do to get a little bit better at what I do. In terms of modeling, resolution, of course, decreases with length of time, like most models. So the further out you go, I would say within 3 days plus, modeling clouds is not very good at all. I would say pressure is modeled a little bit better. I would say temperature changes are. Clouds, precipitation, a little bit of a different story just because of how much of a chaotic system comes along with that opposed to just straight air masses being merged, which essentially is what a frontal boundary is. What you want to see throughout modeling is similarities. So for example, if we're forecasting something within 3 days, we want to use the short range models, the high resolution rapid refresh and the North American model alongside the Canadian model. And there's some others mixed in there too that we use. if you see that these three models all have the same thing, which they actually would for today, they would have a clear sky, beautiful sky, then you know the forecast is good. If you got two of them on one team and then one other on another team, we pretty much see that day in and day out. So we got to determine what factors we might know in the forecast that could alter what those outputs actually are. So, for example, if the fog deck is still on this one model and we expect it to be burnt off by now, but that one model actually has it, and that's going to influence our temperatures, then it might be on to something. So using kind of your intuition, your knowledge to make informed, educated guesses is essentially what we do. It's a lot of educated guessing each and every day, but it's to get you the best product we can. And it's all kind of comes together and meshes at some point. So short range models, if you do head to that pivotal weather site, look for the HER. That'll be the number one you find. The NAM has some tendencies that really bother me. And then the Canadians actually do a pretty good job with modeling cloud cover as well. In terms of long range modeling, you've probably heard of the GFS and its issues as well. I'm a meteorologist, so I can chirp all these models day in and day out because I've messed up my forecast several times. So the GFS, the Euro, two major global models, that's kind of in terms of a time frame, we get above 3 days to within a week. I would say past a week, things are very, very iffy overall. And then this is the younger Canadians' older brother. So you can kind of see this more as a low resolution version of this smaller resolution Canadian run here, which is actually very helpful for us. So each model, of course, is parameterized to a place where what we see is kind of more of a Canadian weather pattern here, living in the northern United States. So while the European model is a very good model, the Canadian model is also very useful because they're actually not forecasting and setting this model too far away from where we're at right now. So the Canadian model is something I've been long a fan of. The ICON model is a German model that also has some pretty good outputting, usually for tropical systems pertaining to that. All right, so we looked at the models. Look like we're going to see some sort of cloud cover, but now comes some question marks in the forecast. All right, is it going to be high clouds? Is it going to be low clouds? One of the things we can do when we take a deep dive on that pivotal weather site, on that tropical tidbit site, you can actually click the screen anywhere on the map, and what it puts out is called an atmospheric sounding. So I showed you a sounding or a temperature profile earlier today, but all that was the entirety of the atmosphere. So now we're down in the troposphere, which is the lowest level of the atmosphere, that lowest layer, and what we're seeing here exactly is the temperature once again, but this time we have this green line, and this green line is the dew point. So what did we learn earlier? Dew point, temperature, those two meet up, and exactly what we see is potential for cloud cover to develop. So you take us at the surface level here, we got an air temperature of 48, a dew point of 44, and like we know, temperature as well as dew point both decrease with height. So we head up towards around, I think that reads 1 kilometer and 3 kilometers there, and we find an area where that red line and that green line are meeting. And essentially what that means, dew point, temperature, it's equal. So this is a very good sounding for low-level clouds, or I'd say low mid-level clouds overall. Where we do see these lines get close, but not entirely meet, that's where it gets difficult. You want to look at frames. This is an hourly output from this model, so essentially think about it this way. If the model has every 15 or 30 minutes is putting out a graphical output that you can see the clouds, to see the rain or precipitation on the map, for every one of those data points is one of these. And thankfully, we actually have free resources where you can actually see these things and make a deterministic idea yourself. So if you're seeing that for one frame, maybe a little bit cause of concern. If the next frame has those two lines a little bit closer, then there's potential to see more of those mid and upper level clouds, opposed to if these lines were further apart. Now we know there's no cloud deck here through, I would say, roughly 4 to 7 or 8 kilometers, but we do know there's a very good chance at low level clouds. So essentially, that's what we would know at that exact instance. This is a specific time essentially. So this is an 8Z model run here at a specific, of course, coordinate, and then the time frame of when that exact data point is. So at this time, we would know that there's a good chance for low clouds. I would say a decent chance, at least for some high clouds. Only necessary with harder forecasting. One of the things that you can do with this, that I was talking about, a limitation with satellite data and observations on the ground, is if these lines are close together here, the only way you know there's clouds there is to have a sounding that would be coming together in that area. So essentially, this is a way to find clouds that are squeezed in between the top layer clouds and the bottom layer clouds, or just have a better idea if clouds are going to form in the first place. So that's a skew-T diagram, otherwise known as a meteorological sounding. Dew point equals temperature. We get the cloud formation. There's other forecasting techniques too. It's not just modeling that we talk about here. We use statistical and historical data, model output statistics, the national blend of models too, which is a little bit of a different situation than just the weather modeling itself. So we can use those things to solidify our thinking, back up our thinking, and give a little bit of some historical context, because things do happen differently in the past. If the model knows that, it can project something a little bit better. And if you know that and the model's not projecting it, then you can actually say that. And there's certain times and places where that's very beneficial for us meteorologists, kind of knowing the history of places. Like, we know if we're going to be getting a large coastal low, Narragansett Town Beach is going to be getting some pretty good swell. We're going to be seeing the waves splashing up. Things like that. There's localities to weather that I'm still learning because I'm young here, that definitely help us out. So in terms of the forecast creation, final thing when we're forecasting clouds, what is the conclusion for the hours and the days ahead, and what can we expect to see? Of course, this is me doing my stuff on the green screen. You can see some clouds here throughout parts of southern Rhode Island, but I like to try to differentiate what type of cloud cover it is. I don't always have time, and obviously it's not always beneficial to the viewer because they care whether or not it's pretty much just sun or cloud in the first place, which essentially is the same thing you guys really worry about too for viewing purposes. So what's the conclusion at the end? How can you use this knowledge to your advantage? You know that sounding and a little bit of that cloud deck coming in around 3-4 a.m. tomorrow morning, maybe make it so you're viewing a little bit earlier than that, so you don't even have to play that risk in the first place. Every forecast has a different confidence level. Let me tell you, winter storms have a very low confidence level. Those are very difficult to predict. Sunny days like today, very easy to predict. Mark and I literally were talking about this the other day. We have not changed our numbers for this weekend forecast for like 4 days now, which is something we do a lot when we have something like a frontal boundary pushing through the region, because those modest changes can have a big effect on what actually happens in terms of meteorology. While we don't reference, I would say, NOAA and other weather sources for our forecast, very important to compare your composition to what others are thinking. If you think you're that good and your forecast is so stellar that you're just better than them all, no, there's other people. The National Weather Service has 5 people forecasting constantly for the majority of their time frame. So that means it's very good to compare what you're thinking to other sources. NOAA, the Weather Channel, AccuWeather, the Weather Network, which is a Canadian source as well, to just kind of make sure you're right in the thinking, because it's very important. And if someone else is seeing something, then you can potentially eliminate that, being like, I think that's going to happen, so that won't happen what they're saying. Or you can also think, oh, I didn't really account for that. I may have to put that into my forecast too, at least have a better sense of why something may happen if it ends up occurring. So comparing your forecast, I would say, is very important, at least for us, to make sure we are all on the same page. And we're constantly in communication with National Weather Service. We use the Slack program to communicate directly with them, see what their thinking is. We read their discussions all the time too, just kind of a better idea of what exactly is going on. It benefits not just us, for them too. We're kind of the backbone of how they get reports and things like that too. So mutual benefit here with the Weather Service. So in meteorology, knowledge is content. We do not use teleprompters. People think we do. If we don't know the forecast, we literally have nothing to talk about. It's pretty crazy. You got to think about it that way. We go up there and we're talking off the dome 24/7. It's not like we're reading off a screen where people are telling you exactly what's going on. So if we don't know our academia, we do not know exactly what is going on. And honestly, that's when you see people stutter. That's when you see people repeat themselves. I have a bad habit of repeating myself in the first place just because I talk a lot. But yeah, if we don't know the forecast, you don't know what's going on. And it's kind of the same, I would say, essentially, if you're looking up at the sky, you're doing some observing, you can look at weather.gov or the Weather Channel, but if you have some intuition of the forecast, you may actually have a better idea of why something happens, and that could benefit you in quite a different way. Press the wrong button. Some things to remember: weather always changes. It's just as important to keep up with your forecast as it is to create it. Forecasts change; they bust all the time. Little factors, such as, I would say, unexpected fog. I know it's an example I've used a few times, but it can really negate things. Like, for example, if we have a big thunderstorm event being portrayed for the afternoon with a cold front arriving, and there's all this sunshine, but then we get the marine layer rolling in, and that lasts like 2 hours, I'm not too high or confident that I'm expecting severe thunderstorms later that day, because what the fog does, it kind of negates the majority of those things. That kind of creates the energy for those storms to spark. So adjusting your forecast as necessary is very, very crucial to portraying what actually will go on and keeping your viewers involved in what's actually going to be occurring and being right, which is, of course, our goal. Forecast accuracy logarithmically decreases with time. So it's not an exponential decrease where it's terrible the next day, but essentially what happens is a slow decline. But once you get beyond that 7-day mark, things go crazy, especially with some of those global models. GFS, notorious for having a Category 5 hurricane on like day 8 or day 9 of their model run. So keep that in mind. Forecast accuracy. If you're checking for a wedding, you got a big event. Of course, a day like today, you were probably checking the weather 7-8 days ago. Did it change? Potentially. Not always, but I would just use some caution, especially if you're forecasting well in advance for something that is not so certain. Other things can affect visibility too. Air pollution, something we see a lot with subsidence, high pressure, that's pretty much sinking air. And what we do see with that too, that lines up with wildfire smoke. You can actually see some obstructions to visibility. So we may have noticed this a few times over the summer, the moon being orange, just a subtlety. But what we do see with that is just kind of more of that light scattering, and why these things kind of can be just a little bit of an annoyance in terms of you observing the sky. So in terms of wildfire smoke, there's actually a product on that HER model. That's what we use to forecast that wildfire smoke. So it's another thing you can add if you want to, is that wildfire smoke alongside the clouds. You're utilizing those models, trying to depict everything that may be going on up in the sky. Air pollution, not the same, not really well modeled by any means. And then, of course, light sources. I think majority of you are astronomers, so you would know that being away from light sources, I learned that that's why the Seagrave Observatory moved from downtown Providence out here for the primary. Get away from city lights. Of course, that'll always be beneficial, but there's other things that give off light, like the moon, that can be annoying. Always prepare for the worst. If you assume your forecast to be right every single time, you're going to be disappointed because it's not going to be right. I would say prepare for the worst and expect the best, and that might be happening at some point. But aside from that, don't always feel like you're going to be right. I don't know. I say this all the time. I hate being wrong. I hate being wrong. And then everyone's just like, oh, then why'd you get in this field? Well, I like it. So that's how it goes with forecasting in general. It's a predictive science. It's not something like astronomy, which is fairly certain most of the time. At news stations, meteorologists like us, we act as resident scientists. So we get a photo chimed in, and I was like, what is that? Tell the meteorologist, what is it? Of course, that's an aurora. It's a little bit of a light pillar there. Notable full moons, big ones for our viewers. Solar storms, of course, with how active we've been approaching solar maximum. That's been a big, big topic, and we know how inaccurate the forecasting is for that, which is a big pain in the butt. Hopefully with NOAA's new satellite, they'll get a little bit better at that moving forward. Eclipses, we haven't had a big one, of course, in a little bit of some time here, but we focus on those too. Meteor showers, comets, planetary alignments, and then, of course, space launches and satellites. A lot of people get worried when they see Starlink satellites going across the sky, because a lot of people don't know what they are. Like, is that a UFO? No, it's just the Starlink people. So at my last station, the meteorologist would actually put out, if the Starlink was going to be up, he'd put a little graphic just to make sure he wasn't getting viewer mail and calls in that people are worried about things going off. Space launches too. A lot of these SpaceX launches we've been able to at least see here through parts of the Northeast Corridor. So all these things fall under the meteorologists, even though we're not well versed in them by any means. Additional overlap meteorology, king tides, very, very interesting. And these are difficult to calculate and not always exact. So king tides, a non-scientific term to describe unusually high tides. So they typically occur at the full or new moon, which is actually coming up fairly shortly, and the perigee, which we know is when the moon's actually closest to the Earth, because exactly what's happening is the gravity of the moon is combined with the gravity of the sun to create essentially a tidal wave of certain magnitude and bring water levels 1 to 2 feet above just that normal high tide level. This is always forecasted by NOAA. The My Coast Initiative also does a great job giving us some information pertaining to this. Typically only minor flooding when we see these two interact, but when there's storm surge, there's any sort of big issue kind of arising, and that coincides with one of these astronomically high tides, that could be big, that can lead to major issues, because you can just add essentially 1 to 2 feet of storm surge to what potentially is already a water level rise and already potentially severe. So that's one thing we talk about. The other thing is 2 seasons. This is a big pain in our butt because everyone thinks that meteorological seasons are more important for some reason. It's kind of funny. Meteorological seasons do not actually line up perfectly with the temperatures that you would expect. You would think meteorological fall through the middle of it would be that like 75th percentile of temperature. It's not the case, even though they are based on temperature cycles, pretty much because there's less variation and because it just includes 3 months. So when we're doing our statistical analysis for the end of meteorological winter, we know it's just going to be December, January, and March, and that's that. We don't have to talk about when the equinox was this year, when the solstice was. But of course, that's also very important for our seasons, the astronomical seasons. Based on Earth's orbit around the sun, of course, that varies a little bit more year to year, but it does make it difficult for us meteorologists to compare statistics. That's why we use meteorological seasons in general. And I say that the scientists prefer seasons, but it's a little bit of your own opinion pertaining to that. We got to explain these things to the general public. Equinox, solstice, I'm assuming majority of you actually paid attention in your younger science classes. But yes, a summer solstice, of course, something we saw back on the 21st of June. Longest day, shortest night. That's when the sun is directly over the Tropic of Cancer. Those rays are most direct over us. So you can think of that in an astronomical sense, and that's what's going on. But we also got to think about it in a meteorological sense. So we have our peak sun angle. That means our ground and our atmosphere is being heated to the maximum. So essentially, that's why we see the most active time for severe weather is in the late spring, close to that summer solstice. Also has different impacts on heating bodies of water, things like that. Of course, you head into this time frame, the equinox. That's where you see the sun's most direct rays pass over the equator. We see equal day, equal night. It takes a little bit longer for us just because we're just north of the equator itself. Winter solstice, shortest day, longest night. That's when things get dark and everyone gets hit with sad. So why is the sky blue? Another very important overlap with meteorology. I'm actually going to talk about this for my Sunday science topic tomorrow, so you guys get a little sneak peek. Of course, it's a very good question. Why is it not just black? Why are we not just seeing up into space? Of course, that's what you see with a telescope. Why aren't we seeing it now? Well, the sun emits white light, and all that white light is essentially is a rainbow. But all of the different colors have different wavelengths. So what happens is once that blue kind of encounters our atmosphere, that light essentially is scattered about. Essentially, so that's the only thing we are seeing. All the other rays actually make it to us. But then it gets a little bit interesting because once we shed the blue and the light actually passes through more of the atmosphere, then we actually just get leftover orange and red. And that's why our sunsets are those colors, not blue. So it's a little bit of an interesting kind of phenomenon that happens, of course, each day, each night. But overlaying these things that are meteorologically important with astronomy is kind of some of our jobs. So love you guys. Follow me on social media, whatever you're using. You can see it here. I'm on X, Instagram, Facebook, even on YouTube with some of my information. Not the prettiest photo there, but have some funny stuff too. We get to go out to Gillette and things like that. So yeah, I appreciate everyone having me here today. Hope I gave you a little bit of information pertaining to what exactly I can go back Skycrapers. I don't know how long I'll go. 30, 34.
Yeah, I have a question online.
DJ, I might be interpreting, I have a digital weather station at my observatory,
Yes.
and one of the problems I have, of course, especially in the fall, is dew. So I look at the relative humidity,
Yes.
whether it's high or it's low, but more importantly, I look at the dew point, and if the dew point is close to the temperature that's predicted, then I know there may not be any clouds in the sky, but it'll be raining on my dome and my telescope. I mean, am I interpreting it properly?
No, that's pretty much exactly what's going on. Is what we're seeing is not just water vapor, it's actually that turning into a dew. So once the temperature reaches the dew point, dew forms and you cut it on your dome. So you are interpreting that exactly right.
But my question, another part of this question is it the fall? In the fall is when we all have the most problems with dew on our objectives and everything else. And is that because of the difference between the ground temperature and the temperature of the air, and there's residual heat rising and what have you?
You're exactly right. So we got to think about the equinox and the solstice. In the fall, we get the equinox, and actually overall, just through the fall time, there's more time that we're actually in night than we are during the day. So less of that sensible heat flux, and that's increased. We actually see a lot of daylight in the springtime. So that's exactly why is we have more of a nighttime and more of a time for all that heat to escape, and we get the dew formation. So
Okay, thanks.
Put the microphone for.
Oh, okay.
People want to give you a question. You have a question?
Yeah. I think I read somewhere recently that we're heading to a La Nina.
It's going to be a weak La Nina, yeah.
Now, what does that mean for us in Rhode Island?
So it's a good question. Of course, what that means is overall, La Nina has different impacts here. I love how people do because it can have major implications on weather in certain locations. But all in all, what a weak La Nina means, I would essentially say for our winter time is more in the way of coastal lows developing. We see changes of moisture that goes on in the equatorial Pacific region. More of that is actually transferred into our region. And then eventually we see more in the way of some coastal storms. Also, some of these lows actually have a better time developing Midwest and stall out over the Great Lakes. So that's also another area where you see above average precipitation. But in terms of temperature, it gets tricky with La Nina because you end up on either side of that frontal boundary. Once that low is riding up the coast, it's either snow or it's rain. All in all, I would say do expect more of those kind of potent coastal lows this winter, opposed to last year where we had more of the cutoff lows, just because there'll be more moisture to work with overall. That's essentially what La Nina is doing for us.
We got one question in chat from Greg Shanos while you hand that.
My question is regarding the jet stream, because the jet stream astrophotography wreaks havoc, especially in planetary. Can you comment on that? Is it in the troposphere, the stratosphere, and what is it exactly? And
So yeah, the jet stream, of course, it's kind of our the jet stream is kind of our driving factor in terms of all meteorology. You got to think about how I was talking about the atmosphere being a fluid. So within a fluid is a bunch of waves. The biggest waves we have, they're called Rossby waves. And essentially, that's what drives the jet stream. But the jet stream, it's not down at the ground level, or we'd all not be here right now, be blown away, because the wind is strong in the jet stream. So when you're looking at the jet stream, I was also showing you those soundings, where you can find it in terms of a pressure level. A pressure level would be 200 to 250 millibars up, and that's the same as going a certain distance. I don't know the exact distance, I would say the jet stream is up. But if you're looking at one of those soundings, you can know that between 200 and 250 millibars is where you can find the jet stream. Temperature, dew point meeting in those locations. Yes, there's potential for cloud development. And all in all, if the jet stream is strong, then that means that there'll be more vorticity and more potential to see cyclogenesis, which of course is development of thunderstorms and other convection types and things like that. So a large jet streak, especially at that 200 to 250 millibar level, if it's overdone, then it may be indicating some bad weather is down the line. If the jet streak is weak at that 200 to 250 millibar level, then that's a good indication that overall things should be subsiding and whatever's going upstream should be kind of coming your way. So, Greg, you can kind of look at those pressure levels in terms of what's going to be happening synoptically and big scale weather-wise, but I wouldn't say it's too necessary to be looking at in terms of cloud cover.
Okay, thank you very much.
Yeah, thanks for the question.
Imagine that the town of Garvin and the next town over is Stowe.
Oh, it's got
Tornadoes. How do you predict? tornadoes?
That's a good question.
Astro.
Yeah, so predicting tornadoes. Tornadoes are one of the most, I would say, studied things that we have no idea about exactly how they form. We know the ingredients that are there. We know that it takes a lot of wind shear, which is, of course, the wind. I know you guys don't know this. The wind turning at different levels, not just in speed, but also in direction. We can measure those things on those atmospheric soundings in a little thing called a hodograph. Can be like the tall tale sign. If you see a certain signature on that hodograph, that means there's very good potential for a tornado. So if there's a lot of wind shear in both magnitude as well as direction, which is the change in wind overall, then there's a good chance that those supercells will be turning, and eventually if they turn enough, then you can get one of those wall clouds that would eventually lead to a tornado. But that was a very interesting situation that happened in Harvard and Stowe, because we were talking with the National Weather Service, and Harvard and Stowe are right next to each other. They're essentially town to town, and they actually depicted this as 3 different tornadoes that came from the same parent thunderstorm. One of them actually touched down only about 2-3 miles away from the other one. So you'd think it would be the same tornado, but what we learned, we're always constantly learning as meteorologists, is you need at least a 1 mile gap between touchdowns to call them different tornadoes. So it's a little bit interesting in how that kind of goes in climatology, that would potentially, back in the day, only been 1 tornado added to our count, and now it's 3. So in terms of forecasting that, meteorological soundings, wind shear is the big factor. You can look up hodograph if you want to read one of those, and that's kind of your tall tale sign. If there's enough convective available potential energy, which is also known as CAPE, then those cells can start to get going. Which is kind of the main ingredient. You need the sun. The sun heating up moist air is what causes essentially all things. Thanks for the question.
Nice presentation.
Thank you.
I have a question about pollution. Seems to me in the last few years I've noticed more pollution than we used to have. I don't know if that's really true or not, but what's the status of the, and where's it coming from? It used to come from the Midwest, from coal mines. I don't think we have that as much to worry about. It seems to be increasing to me.
Good questions. I wouldn't say I'm an expert, but I'll try my best. Yeah, in terms of air pollution, something we monitor, air quality index. There's kind of 2 types of pollution. One of them is gaseous. The other one is particle pollution. Particle pollution typically comes from wildfire smoke, which we've seen a very drastic increase in wildfires out west. And that has had implications on our weather here locally. Got to think 2 summers ago when we had air quality values above 150, you could barely breathe outside. So that is definitely on the increase, and statistically speaking has been for a bit of some time now. And then just general carbon is increased, and it's continuing to be monitored to a point where it's not a great outcome. Of course, what we're seeing in terms of our carbon footprint, each other, more people, that's more carbon in general. I think I muted this. Oh, I'm good. All right. Yeah, I just pressed the button. You can use it. Either way, carbon is increasing in our atmosphere, basis of what I know pertaining to that. But definitely the wildfire smoke has been more of a noticeable impact to our pollution in general. I've only been monitoring air quality index now for roughly 3 years. I would say I hate to see what we're seeing in terms of making it so more emissions would be okay to have in our atmosphere. There's nothing good about them. It's not like we have extra plants that need more carbon about anything like that. So emissions are definitely a problem in this country. They're a problem globally in other places too. But in terms of what you're noticing, probably just a little bit more people, a little bit more carbon, aside from the fact of that particle pollution coming from the wildfire smoke. I think that's the most notable thing in general. And yeah, we're a little bit more in tune to it, so we could be kind of noticing it more just ourselves too. Thanks.
Another big particulate generator are automobiles.
That's number one.
Yeah, and you're getting more, more and more cars are on the road every year, and so you're getting more and more particulates. And it's true, right? The particulates have been knocked down from the coal burning power plants who don't have as many of those. Many of those have gone, out of business. They're going more with gas, which doesn't give off any particulate. I used to do some of that.
Yeah, very good.
One of my former lives.
Yeah.
Right? But yeah,
Appreciate
cars are like the number one. Wildfire is big. Cars, right? More cars, more particulate pollution.
Okay, our next speaker, Mark Munkacsy, comes to us from the AAVSO and brings with him what looks like a lifetime of love of observing Brior's variable stars.
Yeah. Speak into the microphone.
So, those of us who are familiar with the AAVSO would know that it has evolved with all manner of gimcrackery for measuring changes in star brightness. Mark is going to share with us how that can be expanded in other ways to further the involvement of us amateur astronomers and make a good handshake with the professional community. So please help me extend a warm skyscraper welcome to Mark.
Thank you.
Scott Weiss.
Once upon a time, astrophotography was really, really hard. It was hard, it was expensive, it required more gear than you needed to just do visual observing. It required experience. There are a lot of lessons learned. It required money. It required fancy mounts. It required fancy software. It was expensive, in case I didn't say that. It also almost required you to have a degree in systems engineering, because the number of different pieces that all had to come together in order to get a good, striking image of the night sky was enormous. But where things are difficult, there is commercial opportunity. And what came along are what we now call smart telescopes. The telescope vendors recognized that there was opportunity in the challenge behind astrophotography, and they went and did their own systems engineering in order to pull all the pieces that were needed into small, compact, relatively inexpensive systems. And there's now a wide variety at many different cost points of the smart telescopes that are available on the market. They have taken off. Sales are estimated to be in excess of 100,000 smart telescopes that have been sold so far. The American Association of Variable Star Observers, AAVSO, has always been interested in how you combine science with what amateur astronomers are doing, and in building a link between the professional astronomy community and the amateur astronomy community. And over the decades, AAVSO has come up with some models and statistics that have held true even with this evolution into smart telescopes that say that anywhere from 1 to 5% of all people who self-identify as amateur astronomers are also interested in doing science as part of their astronomy. And when you go multiply those numbers out on your fingers, you end up with, lo and behold, a lot of smart telescope owners who are interested in doing science. And the AAVSO began to see its inboxes filling up with messages from smart telescope owners saying, I want to contribute to science using my smart telescope. Please tell me how. About a year and a half ago, the AAVSO decided that the correct response is to go study this and figure out what can we do in order to embrace science, maybe with smart telescopes. And they put together a group that they called, with great creativity, the Smart Telescope Working Group, and asked me and Matt Craig, who's a now retired researcher up at the University of Minnesota, to head up this group of 10 to 12 people, all volunteers, a mix of amateurs and professionals, to figure out what's going on with the smart telescopes with respect to science. We started off initially with 3 challenge questions. The first one was kind of how well, quality. And smart telescopes, these little systems that cost a few $100s at the low end, and they provide meaningful scientific measurement of stars up in the sky. The AAVSO, all its history has been dedicated to the measurement of star brightness. And so the natural question here is, if you go up and use one of these smart telescopes to try and measure star brightness, is your measurement meaningful? Does it add to what professional researchers need when they sit down and try and use actual star behavior in order to validate their theoretical models? The second question was an outgrowth of the whole reason behind smart telescopes, that astrophotography is hard, and AAVSO and its observers and members also know that actually going out and measuring star brightness using cameras and electronics and all that bit is also hard, difficult, requires all kinds of fancy software. You do absolutely need a degree in systems engineering if you want to pull together all the different pieces that are needed to come up with a measurement and understand the quality of that measurement to be able to attach an uncertainty to it. So can that be simplified? Because so many of these smart telescope owners are enthusiastic people who don't have a lot of experience with using instrumentation. They don't have degrees that touch over into the field of statistics, which becomes really important when you're trying to use electronics to measure star brightness. Can we make the process of measuring the brightness of a star as easy as smart telescopes have made astrophotography? Right? With a smart telescope, in order to get really cool pictures of the night sky, all you need literally is one mouse click. Now, can we go make the process of measuring star brightness similarly simple? And then the third question is kind of a weird one. It's a weird one because AAVSO, within the last few years, has finally figured out what their actual computer-related costs are. And they have discovered that the cost of membership, annual membership dues, does not cover the average cost of one observer's work with the AAVSO over the course of a year. As a result, the AAVSO loses money on every member that actually goes out and measures brightness in the sky. Now, talk about a disincentive to an organization to grow. And so part of their challenge to us within the Smart Telescope Working Group was, all right, you guys and gals can see what our costs are now on doing computation, on storing images on our servers, on doing backups, on our internet communication costs. Can you find a way that we can go process smart telescope images and extract the science without losing money in the process? So our group in the Smart Telescope Working Group went off to see what the answers are to these 3 questions and a follow-on challenge that came with the 3 questions. In order to talk about this in a little bit more detail, I have to first go sidetrack for just a moment and talk about how you measure star brightness when you're using a camera. So here you see an image of the sky. At the center of the image is the star St Cygni, which is a variable star. If I remember right, I believe it is a long period variable with a period of about 1 year and a change in brightness of almost 6 magnitudes between when it's bright and when it's faint during that cycle. So here you see the image, and we're going to be able to measure the brightness of that star using this image. The first step is to recognize that the image is made up of a bunch of pixels, in this case, something over 1 million pixels, and each pixel has a number that the camera gives you that is a measure of how much light fell on that pixel. Now, one of the coolest things about this process is where technology is today, where even on a smart telescope with a consumer grade sensor in it that only costs a few $100s, those numbers, that sensor, are easily measuring individual photons of light. One of our calibration processes goes in and looks at the response of these sensors, and we do take the numbers that are in there and translate it right down to individual photons. So that's really cool to me. I mean, the human eye is not quite at that level. And that is why we're able to get such spectacular photographs out of today's technology cameras that we're attaching to our telescopes. So here in this case, what I'm showing is a piece of that original image from the prior slide, centered on the center of that one star. And I've put in the numbers that we received from the camera for each of these pixels. Now, things to notice as you look at this, the sky background is not 0. That's due to a combination of many, many things. The star is bigger than 1 pixel. It's spread over multiple pixels. That profile for the star has a tail on it, and you can go out quite a few pixels from that star's center, and you still see a level that indicates that some of the light from that star is spread out quite a distance from where the star is centered. And then finally, and you won't be able to see this from where you're sitting, but if you look at the numbers, you discover, oh, the star is not exactly centered on a particular pixel. The star's center falls somewhere off to the side in one of these pixels. And if you think about it, that's just natural. You can't control the star's alignment onto the pixel grid to any great degree. However, we can go in and determine where the center of the star is in the pixel grid, and we can measure the star's center to better than 1/100th of a pixel. And so in addition to being able to make precision measures of star brightness, you also can do extraordinary things with measuring star position with these cheap little sensors. So if we want to understand how bright the star is, how many photons came from the star, we let our computer start drawing circles. And the first thing we do is draw a virtual circle around the center of the star, and we go add up all the pixels that are in there, and the places where our circle slices through a pixel, we take partial pixel counts. Take the pixel and figure out how much of the pixel is inside the circle, how much is outside, go do that math. Once we've done that, we have all those numbers. We have to remember that those numbers include both the star as well as the sky surrounding the star. So we need to subtract out what that sky background looks like. And we do that with a ring that we put around the star and go inside that ring and look at the numbers that are in there. And that will give us a measure of the sky background. Once we know what the sky background is, we subtract the background from what came up in the center square or center circle. And that tells us how much extra light is associated with that star. The final step of the process is to go pick a star on that image that we know the brightness of. And then by comparing the number of counts that we get for this star compared with this star, we can go figure out the ratio of their brightnesses. And from that, you figure out what the magnitude is of the variable star. So that's the process that we follow. What I just showed is simplified from what happens with a smart telescope because astrophotographers love color images. Not a single one of the available smart telescopes offers a monochrome camera with their smart telescopes. So all of the smart telescope offerings that exist today have built-in color sensors. The color sensors do their color thing by taking all the pixels, breaking it up into clumps of 4 pixels, and they put different colored filters at the pixel level on those 4 pixels. So one of them is colored red, one is colored blue, and 2 of them are colored green. So when we get all those numbers out of the sensor in a smart telescope, we have to keep track of which numbers are associated with the blue pixels, which are associated with the green, and which are associated with the red. And that throws a real wrinkle into the process of figuring out how bright the stars are. So our working group went off. We started gathering smart telescope images. We now have a library of something pretty close to 100,000 smart telescope images specifically curated as examples of using smart telescopes to try to measure star brightness. And what we've learned from that is that if smart telescope quality is good enough, there's an extraordinary amount of good science that you could get from smart telescopes. Smart telescopes, and here I've got the curves up for the C-Star S50, which I know I've got one in the trunk of my car right now. There's other ones out here on the lawn outside. It's a common, good quality smart telescope. It can quantitatively observe stars from roughly magnitude 8 down to magnitude 14 in a single 10-second image. If you stack images, you can get down to about 16th magnitude, 16 plus. Again, using just 10-second images that you're stacking. With the C-Star, you have the option of going up to 30-second long images. We've done some predictions of what that will look like if we try and extract science from it. But quite honestly, we're overwhelmed with the opportunity that sits here with the 10-second images, and it's easier to get a good 10-second image than a good 30-second image with these things. So that's what we're living with for the moment. If you go brighter than magnitude 8 or 9, the stars saturate, they're no longer linear in the response of the sensor, and you really can't use that as a brightness measurement. There are some tricks you can do, but now we're getting back into the realm of experience and understanding advanced techniques and fiddling around inside the settings of your smart telescope. And as one of our members who has a Celestron Origin smart telescope learned, some settings that you can get to and change, you can't undo. So we've become very cautious about going in and fiddling with settings of our smart telescopes. So that first question was, what kind of accuracy is possible with the smart telescopes? And to answer that, I'm going to introduce a number line. And across the center of this, we have this blue number line where really crude measurements are on the left-hand side of that number line, where your measurement accuracy is around 0.5 magnitude. And at the right-hand side of the blue number line, you've got really good high-precision measurements. The green arrows kind of show the different realms that exist. On the left-hand side, there's an arrow that indicates visual observing. An untrained observer is easily able to distinguish color or brightness differences of 0.5 magnitude. A trained observer, someone with maybe 1 or 2 years of experience at the eyepiece out under the sky trying to estimate star brightness can get down to about 1/20th of a magnitude, the 0.05 magnitude end of that line. That's pretty good. And the AAVSO for decades was extraordinarily proud of all of the visual observers that contributed to this kind of data quality within their database of now tens of millions of observations of variable stars. The bottom green line represents what can be done with monochrome cameras and typical backyard, moving up into the realm of meter-sized professional telescopes, where it goes roughly from that 0.05 magnitude uncertainty at the left-hand edge, all the way down to better than 1,000th of a magnitude in estimating star brightness. In between those two arrows, we have the realm of the color cameras. So one-shot color cameras, whether it's your family's DSLR camera that you put on a tripod and aim it up at the sky, or one of the dedicated, even pooled astro cameras attached to a telescope. They all tend to fall within this range. We found that by carefully choosing how we went to analyze the images after the image was made, we were able to achieve a quality level that corresponds to the vertical orange bar. A little bit better than 0.02 magnitudes. All right, so how do we put this into perspective? First of all, it's better, significantly better than what you can do with the human eye. And by the way, that human eye line says nothing about telescope size. That line is the same whether you're using naked eye to estimate stars in the night sky, or whether you're sitting at a meter class professional telescope looking through the eyepiece. That's still the realm of the human eye. That's all about human eye response. So we're down here. This is actually better than the average quality of the measurements that are coming into the AAVSO's database today from the amateur monochrome camera community. And we were a little bit distressed at that. Well, distressed and delighted. So we're a little bit distressed at how come the average for this bar for the AAVSO's community was so close to the left-hand edge. We were delighted that we were able to get the orange bar for using a colored camera so close to the right-hand edge of that bar, and asked ourselves, why? Why is our average for monochrome cameras actually worse than what we were able to get as a working group out of our color cameras? And when the dust settled and we were comfortable with our answer, we realized that the difference was consistency. That across the amateur AAVSO observer community, we have many different telescopes, many different cameras, many different software packages, many different techniques for doing analysis. We have many different ways of uploading data to the AAVSO, and for every change within there, there are error sources. Within the work that we were doing, we discovered fairly early on that we needed to get internally very self-consistent, very disciplined with how we were using the smart telescopes. Otherwise, our data was absolutely miserable. In fact, initially, we were seeing results that were significantly worse than what you could get using the human eye. And as we went and worked and understood that better and managed to eliminate those error sources, through that discipline process, we found we could get really good results. And that became part of the findings of our group. One of the curves that came out of our group is this one. It shows the improvement in measurement accuracy of star brightness as you average together multiple exposures. So because these 10-second images are so relatively short, it's really, really easy with a smart telescope to grab 20 or 30 images. This graph is for a total of 30 images and shows how your errors drop as you average together more and more of these 10-second exposures that are all included in the total of 30 that you've obtained. As you go to the left-hand side, that residual error back down from the individual images that you're getting are worse than what the human eye can do. But what we can do here that you can't do as easily with the human eye is average them together in order to drive away those error sources that are truly randomly behaving. And as you do that, you see the curve drop and come down here as you move off to the bottom. And so we learned, well, I talked about how good you can get. We learned averaging images together, or measurements from images, is really important. We don't actually combine the images. We take measurements from multiple images and combine them. We found it's really important to take into account color. And for those who have ever tried their hand at measuring star brightness, taking color into account, star color, is a real nuisance. It involves spreadsheets, it involves gathering data on special stars, et cetera, et cetera, et cetera. We discovered that you can substitute quantity for quality. And by using the smart telescope to get measurements of hundreds, in many cases, thousands and tens of thousands of stars, average all that together, and we got results that were better than what we were getting when we were hand-picking stars specifically to help us with those color kind of corrections. On that earlier image where I showed you the variable star and the comparison star, we had one comparison star, we had one variable star. We took the ratio of the two. We discovered that on images where you've got a few thousand stars captured in the image, you can use all 1,000 stars in that image to help be your brightness reference. And you get dramatically better results by doing that. And then, as I already mentioned, the sensor is at the root of a whole lot of these issues. And so the answer to that first question that the working group was given is yes, you can do good science using smart telescopes, but you have to be smart about how to use the smart telescopes. I'm going to take those three questions we had and take them a little bit out of order and talk next about the efficiency question. And remember, that question was, can we reach the point where we're not losing money within the AAVSO on every observer that goes out and uses their smart telescope? And one of the schemes that we came up with that seems to work really, really well is to use the little computer processor that's in the smart telescope to do part of the job before the data gets sent to the AAVSO. By taking advantage of that dramatic parallel processing capability that exists as each one of these little smart telescopes with their little processors, you know, kind of capability you have in your smartphone, maybe. We were able to get a lot of pre-processing done before we asked AAVSO computing resources to handle the rest. And so what we do inside the smart telescope is convert that original image over into what we call a star list. The star list is a human readable list in text of all the stars that are found in the image, along with brightness information, the information from those circles and adding up all the counts within those circles. That requires orders of magnitude, you know, 2 or more orders of magnitude, less processing bandwidth, less internet bandwidth, less processing resources at the AAVSO end to process than accepting raw images from observers. So instead of having raw observers load their image into AAVSO resources, which is what happens today for observers loading up images to process them, we instead have the observer use their smart telescope, single button push, in order to convert the image over into a star list, and then the smart telescope, all of which are connected to the internet, uploads its list of stars to the AAVSO, where we go through the calibration, the averaging, the different correction factors that get applied to it in order to come up with a measurement that then goes into the AAVSO permanent archive. The observer can log in, take a look at what's going on with the process, see their results, download their results if they want. But it significantly reduces the processing load everywhere in the system. We've now been using star lists exclusively within the working group for well over half a year. And they've turned out to be really useful even for us. We found in the process of doing it that it's also useful beyond the realm of smart telescopes. We now have regular telescopes where we're using this idea of a star list as an intermediate form that's got a well-defined standard interface that serves as a data exchange format within the astronomy community. And we will very, very shortly be publishing it as a standard so that everyone is able to be using the same star list format as they go into their work. So we found the answer to that third question was also a yes, we can make it cost effective. And that leaves the second question, which is, can you make the whole process simple? And this is a little bit more complicated. and the reason it's a little bit more complicated is that as we were working through the techniques that were needed to get those extraordinary good quality measurements out of our smart telescopes, there was a lot of fine tuning that we were doing. When we first put together our internal tool set for doing that quality analysis, there were over 64 different ways of going from the image to the final measurement that we had identified. And we explored all 64 of those different paths. And it wasn't quite as simple as saying, hey, in every single case, this path ends up being the best path. So there's some compromises in there. And one of the questions we had to deal with is, can we come up with algorithms that correctly choose a path through there that gives us good quality results in the end? Some of these algorithms that we were coming up with were brand new. Some of these algorithms were dependent on understanding error sources that we still, even today, only understand at a very fuzzy level. But it looks like there is a way of getting from the original raw image to a final measurement that does not require does not require wisdom and experience in order to find the right way from the left to the right. That you can turn it into an algorithm that picks, if not the best way, a good enough way in order to get to the end product. So, and then the final observation was that the state of the art in doing image quality assessment and even measurement quality assessment is not quite separate from having a human in the loop. There's still so many things that can go wrong, even with a smart telescope. And that's everything from satellite trails that happen to go through an important star in the image, to intermittent clouds where clouds are not uniform over the image, to, we had one case where our algorithms could not handle the dog. The dog kicked over the telescope, sitting there with a little tripod. And the algorithm went and tried, and actually it did come up with what it claimed was a measurement from that image. So there's still places where we need to get human eyes in the loop. We're kind of optimistic that within a few years, we should be able to cut down on that. But at least for the time being, there's a bunch of things where knowledge of what was going on in the environment is useful in understanding measurement anomalies as you go through that.
Question.
Yes.
Why aren't the observers being coached to just throw out those particular images?
The general reason is that on smart telescopes, there really is no easy way to throw out an image. The smart telescope just has a button that says go. And it goes, and it continues going until you hit the stop button.
Mark, I have a smart telescope, the Sea Star, and I noticed that I can accumulate all FITS files.
Yes.
And would it be useful, as far as coaching people, to have them review the FITS files to throw out the satellite trail or the dog bumping into it or whatever? Or is that just making it too complicated?
So yes and yes. So there is value in being able to go through your raw images and sort through them and say, this raw image is better than this raw image needs to be thrown away, et cetera, et cetera. However, as you go look at the online forums and listen to the emails that show up in the AAVSO's inbox, you discover there are a fairly substantial subset of smart telescope users that have no idea where to go to find the raw images. You have to take your smart telescope, you have to hook it up to another device, then you have to go through with some kind of a file explorer thing in order to navigate through the directory structure in order to find where you're going. And the different smart telescope vendors have arranged their directory structures differently. So the instructions end up being specific to one telescope type, which makes it difficult to do webinars to give everybody insight into how to do this. So yes, it can be done, but we're trying to find ways that don't work.
That's more of an advanced technique.
That's more of an advanced technique. So let me give you my final thought here, which extends a little bit beyond just those three questions that we asked, where the answers end up being positive to all three of them. The next realization that the working group had in conjunction with AAVSO leadership is, in order to truly make this a single button operation, the AAVSO needs a software suite that can process the star lists coming in from smart telescopes, where you don't have the luxury of being guaranteed that somebody has gone through and taken out the images that are clearly bad. So you got to be able to recognize, and you don't have the image, so you have a star list. So you have to recognize a star list that came from an image that you can't trust. Figure out how to probably treat those things, figure out how to do calibrations, figure out how to deal with arrival time of the star list. They're going to arrive out of order. You've got, by our estimate, as many as 1 million star lists a year that the AAVSO can expect to receive. And keep track of all this again and keep the cost reasonable. And so right now, our working group is off building, again, with a bunch of volunteers, this processing capability that will enable AAVSO to augment its current measurement techniques and interaction with observers to be able to fully embrace what can be the science that can be done with these smart telescopes. All right, questions?
More. Do all smart telescopes have the ability to do the starless conversion?
So,
That's okay.
yes, okay. So the question was, do all smart telescopes have the ability to do the starless conversion? The answer is absolutely no. Today, none of the smart telescopes can do it internally. We are in the process of working with the different smart telescope vendors to come up with plans and schedules for them to be able to include that in there. In some ways, my heart goes out to these smart telescope vendors. They are trying to deal with the world of tariffs and how tariffs affect the sale of smart telescopes and their future. And then along comes Munkacsy and this other group of AAVSO people who want to talk about changing the software. Let me tell you, this is so low on their priority list right now that we struggle to get their attention. But there are a number of them who I'm not going to publicly advertise at this point, who say that they believe that they can go fit this in. They're eager to do it. They want to have the option of offering their customers a science program that can go with the telescope when they go buy the telescope. And that's what we're trying to work out. So we're not there yet. It's all being done currently with external tools.
The mind is a wonderful, the human eye and the mind is a wonderful image processor. Have you tried creating virtual images out of the star lists?
Ha! Oh, that's a great question. Yes, that was one of the first tools that we put into our tool suite, was the ability to reverse engineer an image from the star list. That worked fairly well. One of the numbers that we track, we've learned we have to track, is what we call a false alarm rate. That is how many stars show up in the star list where there is no star in the sky at that location. So it's caused by noise, it's caused by whatever else shows up. And we try and tune the whole process to control that number. And right now, our belief is that a number around 15% is a good number. That 15% of all the claimed stars in an image are not really stars. We can live with that. Where we run into problems is when the false alarm rate is up around 80%. So you have 4 to 5 times as many false stars as you have real stars. And it's not hard to have that happen. And that's where the human eye becomes really useful, because the human eye looks at that image and says, well, obviously that's not a star. But in most cases, we've been able to get to the false alarm rates that we're comfortable with. For some reason, and I don't really understand why, maybe I should be scared by that, we don't have the opposite problem. We don't have false negatives where the algorithms are failing to declare a star. It's all that background noise in the image. It creates
Noise is always positive in your case.
Yes, in our case, noise is always positive. Yeah.
Thanks for the very nice talk and very exciting work. Can you describe in more detail the product that comes out of the one-shot color sensor? So I understand that each pixel has 4 subpixels in the RVGG. Do the smart telescopes store the R-only information, the G-only information, or is it some sort of single number calibration?
All right, that's a great question about what actually comes out of one of these color sensors. And the easiest way to understand what comes out is to understand how the color sensor is made. They start with a monochrome sensor. All the electronics is monochrome sensor electronics. And then they overlay these color filters on top of those pixels. So what comes out from the electronics is just a pixel by pixel count. And if you go in and look at the pixel by pixel counts, you keep track of which pixel has which color filter associated with it. So you know, for this particular Sony chip that C-Star is using in it, that the very first pixel count number you get out is going to be a blue number. And you know that the one right next to it is going to be a green number. And then you know, boom, 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 all the way across the row. And then in the next row, the first number that comes out is gonna be a green number, and the next number that comes out is gonna be whatever one I left out, red or blue. And you keep track of all that as you go through. Now, traditionally, when you want to create an image for the human eye, you would take that image and create 3 or 4 sub-images by taking just the red pixel numbers, take all those out, put them into a picture, take just the blue pixels out, put them into a picture that becomes your blue, take just the green ones out, put that into a green image, then blend the 3 images together, and now you have a color image. The traditional way of handling color images in the science world, well, number 1 is don't do it. But number 2, if you have to do it, is to break it apart into those 4 images, 2 greens, 1 red, and 1 blue, and handle each one separately. When we went in and did our error analysis, we discovered that is the worst possible thing you can do if you're interested in actually getting measurements out of the image. You are much, much better off either completely ignoring the color information and just treat it as a monochrome sensor that's kind of been damaged. So your pixel response is not uniform, but you say, I've got so many pixels in there, I'll just average it all out. And that turns out not to be bad. Or to go in and use algorithms that understand the pixel color sequence and don't work independently, but work interdependently on the colors together. And by doing that, we were able to get results that pretty much matched the results that we got when we treated it as if it was a monochrome sensor. So there's different ways of doing it. And that, quite honestly, is going to be one of the biggest stumbling blocks we have with the smart telescope vendors, as we're talking to them about treating color differently than they've ever treated it before. And they're looking at us and say, well, we outsource all our software. How are we going to do this?
Actually, okay.
Then after that, we have one from Greg Sheen.
Okay, thank you. So the question is, so when you're working with the smart telescope, which is here on Earth, how does that relate to the telescopes with the sensors that are used, the imaging that's in space? So when you're taking an image from space, what are we seeing differently? Because obviously the atmosphere is the factor. And then the second question I have is this technology, the sensor itself, monochrome or color? I don't even think the color is important, but the monochrome sensor, how long has that been around? Because I think when we went to the moon, when we took pictures of there were no stars in those images, and one of the issues is they said that the sensors weren't, the cameras weren't technologically advanced to be able to filter out that starlight correctly.
Thank you. All right, so let me start with the second question. The second question, which is going back to old technology there, the number you're really asking about is what we call dynamic range. The difference between the brightest thing that you can register with the camera and the faintest thing that you can register with the camera. And what sets those two limits is the amount of noise in the camera at the faint end and the nonlinear effects that come into play at the bright end. In the smart telescopes, pretty much without exception, what is limiting their dynamic range is the number of digital bits that they use in their analog to digital converter. That's they're taking the actual count photon, or the electrical charge associated with the photons that get collected in each pixel and turns that into a number. Most of these sensors are using 12-bit converters. So you've got that's 16,000 roughly as your maximum count that you can get out of one of those sensors. And that sets this dynamic range. The underlying technology being used goes back to Einstein and the photoelectric effect, where you have photon knocking in electrons. The only thing that's changed since the very beginning of our electronic camera era to now is how we collect those electrons and how we count them. Our technique for counting them really hasn't changed in the past 3 or 4 decades, except for a little bit of noise reduction. The technique for actually collecting the electrons has gone from vacuum tube technology over through a couple of generations of semiconductor technology. So we now have the same technology being used in the camera in your smartphone as is used as the underlying technology in today's frontline, top-of-the-line space telescopes. It's still, the physics at that underlying sensor level are the same. Where you get a difference is in the dynamic range that's available to them, in the optics that's available to them, and in, as you pointed out, the atmospheric effects. And in the case of space telescopes, it's those atmospheric effects that are huge that they're able to take advantage of, that give them so much better precision than what we're capable of with the surface.
Time for one more question, Dan?
Yeah, we got Greg Shanos.
Yeah,
Okay, all right.
I have a question.
Sorry.
Can you run through how the
the software and the sea stars or any of the other ones will generate a star set? So my question is there an external program that will take image or images and generate a star set?
So right now we have engineering prototype level software that does that we're using internal to the Smart Telescope working. It is not user friendly. And so it's not ready for any wider dissemination. However, we're coming to the realization that there are going to be situations where something like that will be necessary. And we're looking at several possibilities for doing that, whether it's a standalone program that runs somewhere, whether it's something that we pack into a browser, so you do it invisibly, kind of from within a browser, or whether there's a way of, one of the cooler ideas that a number of our folks don't like is a little add-on box with a little Raspberry Pi in it that you just plug into your C-Star. And it sits there all night long and it watches what's going on in the C-Star. It understands the folder structure within the C-Star. So it pulls out the images as they show up, it converts them over into these star lists, and it either connects to AAVSO and uploads them right as you go there during the night, or it saves them until you leave your dark sky location and are plugged into the room. So, yeah.
And we got Greg.
Okay, I think you kind of answered a lot of my question. So when the program is ready, we download it, and like, does it need the I have the C-Star S30 and 50, and you see the aligned and stacked image on your iPhone. Is that what you're using? Or are you using the FITS files that are saved in the C-Star, and you got to download those into your computer? And that.
Hear the question. It was all of these smart telescopes are really good at stacking images in order to increase effective exposure time and make your astrophotographs pop out.
Right.
They also make available the raw 10-second images that contribute to that stacked image. Right. And the question was, what do you use when you're doing measurements? And we have found that it is very valuable to have both when we go to do measurements. I've even got the right slide up here. When you use the stacked image, you pick up at least 2 more magnitudes of sensitivity, which enables you to get to fainter stars than you otherwise can from the individual images. And that's great. However, if your star shows up in the individual measurements, you really benefit from the averaging effects. that occur by averaging the results from many, many, many hundreds or even thousands of raw images, they will give you a better averaged measurement than you will get from one measurement from a stacked image. So
now, will we see the results in our downloaded program, or the program just collects the data, uploads it to AAVSO, and you do all the number crunching to determine the magnitudes? How does that work?
So the question is about how the observer sees all this playing out. And I'm going to laugh because I'm the one with the microphone. Different members of the working group have different opinions on how this is going to work. So my opinion on how this is going to work is that the data is all going to get pushed into the AAVSO. There's a final measurement that's going to be made within the AAVSO, and it gets archived in here. And then after the fact, the observer or the researcher are able to go log into the AAVSO and view raw data or view average data, view collected data, view data from one telescope, view data from all telescopes. There will be a variety of ways that they can see what's going on. And individual observer can download their data in the form of a spreadsheet and do their own studies using their raw data. There are many AAVSO observers today that do their own research, and they use their observations for their own research and also put them into the AAVSO archives so that other researchers have them available. And so we're going to try and support both of those models as we move forward. Whether you download software or whether there's software embedded in the browser or whether there's software embedded in the smart telescope, I think the answer is going to end up being all of the above. And it just depends upon which vendor, which smart telescope, where you're located. You know, if you've got no internet connectivity, the answer for you is going to be different than for somebody that's sitting in their heated home with a cable that runs out to their smart telescope so that everything is interconnected. Completely different environments in those two cases. All right.
Well,
Thank you,
folks. But Mark, that was excellent. Thank you so much. Our next speaker is going to address us on one of my favorite topics. You're going to be talking about the Hubble tuning fork, right?
I'm kind of tangentially.
Okay. The topic is obvious, so please help me welcome Raymond Simon. Thank you.
Okay, it's a pleasure. I'm not getting feedback. It's a real pleasure to be here. I really appreciate the warm welcome that I felt today. I don't know if that's the weather or just the natural tendency of the group, but I get a really good feeling. So I joined the Providence College faculty 1 year ago and moved my family out to Rhode Island. So as a Rhode Island citizen, it really heartens me that a group like this exists. And I plan on staying involved over the years. So I'm really excited to be here. The topic that I thought would be interesting to discuss today is the topic that makes up my research domain, which is the formation of galaxies over time. I'm going to pare this down to a more manageable question that we can approach in 45 minutes. But what I want to do is tell you the story, the emerging story of how systems like the one I'm showing you here take shape over the 13.5 billion year age of our universe. So I'm going to start. Let's see, read that. I'm going to start with this simulation. So what I'm showing you here is a 20-second loop. It's showing you the last billion years of a simulation that has run over the full lifetime of the universe. The end product of this simulation, we hyper focus on a single system, is what I will refer to as a well-ordered disk galaxy. By that I mean it has the following characteristics. It is thin and symmetric, and it has low disordered gas motions and high ordered gas motions. That is to say that most of the mass is rotating around the center on a regular circular orbit. If we switch the frame And I'm now color coding by what we refer to as the metallicity. You may be familiar with this concept, but effectively it is the ratio of the heavy elements, the elements heavier than helium, to hydrogen. Okay? The elements heavier than helium we call metals. Take the ratio with respect to hydrogen, we call that the metallicity. And what I'm showing you here is that this well-ordered disk galaxy has a unique distribution. It is more metal rich in its inner parts, and it's more metal poor in its outer parts. So we're going to come back to these measurements over the course of this talk. To prove to you that we're doing something correctly, here's that simulation. And this is a real galaxy. Maybe this is your friend. This is NGC 6814. This galaxy is thin and symmetric. If we were to observe it on its side, it would have a thin structure. If you measure its kinematics, its motions, it have low disordered motions, high ordered motions. You don't have to focus too much on this plot, but what I want to convince you of is that this finding that our simulation predicted, the metal-rich inner part, the metal-poor outer part, is a generic finding for the galaxy population as a whole. So these are results from the MANGA survey, galaxies of different masses, the populations, all of them. I'm plotting on the y-axis the metallicity. On the x-axis is the distance from the center. You can see that the metallicity is higher in the center than the outskirts for all these populations. So these are kind of generic findings for the galaxy population today.
What about ellipticals?
Yes, so these are all star-forming galaxies. This is a key point, is that the population that I'm going to specifically be discussing are galaxies that are still forming stars that have disky structure. There are galaxy population, the elliptical population. These are galaxies that have ceased forming stars.
So these are all spirals.
Yes, these are spiral. They don't all have well-formed spiral structure, but they are all disc-shaped. They all are frisbee-shaped. Okay, so let me back up real quick. This may be a refresher for all of you, but what is a galaxy? That's a large collection of this mysterious matter that we call dark matter that we find interacts gravitationally, but does not interact with light, and normal matter. That's the matter that we know and love, gas, dust, and stars. So here's that image of NGC 6814 from the Hubble Space Telescope. You can see the normal matter popping out. The young stars are shining in blue light. The cold dust is forming this wispy red layer. The center of this galaxy is predominantly old. Those are the old stars that make up the bulge in the center. Okay. So all of this matter is held together by gravity. We live in a disk galaxy, our Milky Way. We live around here about 8 kiloparsecs from the center. From our vantage point, of course, we can't see the Milky Way like this. We see it more like this. And I always show, whenever I'm discussing a figure like this, I always grab a figure from the local community. In this case, it's funny because you may know who took this picture. Mike Kohea? Does that ring a bell? No. Anyway, this is taken over Block Island. This is the view of the Milky Way from Block Island. If you have a beautiful picture of the Milky Way that you would like me to include in future slides, please email me. I don't know, Mike. This was just a very nice picture. Okay, so maybe many of you have seen the Milky Way. What I want to highlight here is how remarkably thin the Milky Way is. We're seeing through the dust lane here. You can see the dust and those background stars that are blocked by the foreground dust. The thinness of the Milky Way is a generic feature for the star-forming galaxy population today. Most galaxies above the mass of the Large Magellanic Cloud that are still forming stars today have this remarkably thin structure and are rotationally supported. Most of their mass is on a regular circular orbit. And so the rotational motion, which we call coherent motion, is one of the key properties of today's disk population. And the question that keeps me up at night is, how did our Milky Way form this structure? How and when? Not just the Milky Way, but galaxies like it today. Why do we have this large population of disk galaxies today? And when did these galaxies form this regular structure? And so answering that question is the major thrust of my research program. And I work at kind of the interface of the observational world and the theory world. So I work with space and ground-based telescopes. You may have recognized a few of those. We have the Hubble Space Telescope, the Keck telescopes on Mauna Kea in Hawaii. The lower left is the James Webb Space Telescope, and this is the ULMA array. I use those telescopes to make measurements of the properties of galaxies over cosmic time, and then I compare those with the predictions from our best theoretical models. If the comparison yields a null result, if we're not producing galaxies with our theoretical models that match the observations, then we have to tune the physics that underpin the theoretical models and try again. So that's the large-scale view of the game. So throughout this talk, I am going to discuss our emerging picture of this question: how did our Milky Way galaxy form, from both of these angles? Mostly from what we're learning from the observations, but it will all be kind of framed around our theoretical understanding. So this is our question, and I'm going to pare it down to a simpler question, which is, when did our Milky Way get its disk? Okay. To answer this question, I am going to ask, when did those characteristics that I opened with, the regular rotation and the development of this metallicity gradient, develop in the galaxy population? And I will also compare with our classic understanding of the answer to this question. Okay. Before I do that, I want to introduce a concept that you may be familiar with, which is angular momentum. So the common way we like to think about this and explain it is that of a figure skater. So a figure skater with her arms out like this will have some property that we call the moment of inertia, which is effectively the mass of the figure skater times her size, and some property that we call the angular velocity. That's how fast she's spinning. The product of the moment of inertia and the size make up what we call the angular momentum, which quantifies the degree to which she's spinning. This angular momentum quantity is a really interesting quantity that we like to study because it is a conserved quantity. That is to say that if the figure skater reduces her size, reduces her moment of inertia, this I term shrinks, the omega term has to get bigger, okay? Because she's not losing angular momentum when she's doing this, in the same way that she's not losing mass, she's not shedding mass. That's another conserved quantity. Okay? So this conservation of angular momentum is a key constraint in understanding how these systems develop spin. Okay, with that in mind, let's discuss the classic model for disk galaxy formation. So this is an old story. The idea goes like this, that in the early ages of the universe, the gas and the dark matter were kind of commingled on large scales. Okay? But that matter was not evenly distributed. So you are sitting here, dark matter and gas, and maybe you have more neighbors to your right than you do to your left. Those neighbors to your right will pull on you in that direction. Maybe a neighbor over here will pull on you in this direction. It's like taking that figure skater and pushing her arms, giving her spin. And so this pile of mass acquires spin through these gravitational forces. Okay. Over time, the gas will collide, it'll self-collide, and it will cool, losing energy. It cools through radiation, and will sink to the center of the dark matter halo. The dark matter cannot collide and lose energy, so it stays as this larger sphere, but the gas will cool and sink to the center. But that gas cannot radiate away its angular momentum. So it has that angular momentum that it started off with from the tidal torques. It loses energy. The result of this process is that it will spin faster and it will form a disk in the center. With time, as more and more of that gas cools, a thin gas disk will form in the center of the dark matter halo. Okay. This is our classic model, and it does a pretty good job at predicting the sizes and the masses of today's disk galaxies. But it is missing a lot of the features that we now know are important for the formation of these systems, We know that stars form in these galaxies and they explode when they reach the end of their life. Those explosions can eject angular momentum outside the disk, in addition to mass, in addition to energy. That's what I'm highlighting here in this pink outflow. We know that galaxies collide together, forming our elliptical population today, but the collision of those galaxies rearranges the angular momentum in a way that doesn't necessarily know about the initial tidal torquing. We know that material is in general just continuously falling onto these systems. So in the ice skater analogy, you can imagine that the skater is drawing her arms in, and at the same time, maybe she's doing a poor job and people are throwing bricks at her from random directions, imparting angular momentum that she did not start off with. Okay. So to illustrate this picture, I'm going to rewind the clock on that simulation I started with from the title slide. This is from a suite of simulations that I work with called the Foggy Suite. It includes gravity, our best model for the large-scale cosmology of the universe, how fluids behave and interact with each other. Stars form and stars die in these systems. And so we'll watch what happens. This is the gas density. So this is very early on. Probably, I think 9 billion years ago is where the frame is right now. And what I wanted to recognize is that early in the stages of the formation of the system, you have little galaxies that are continuously falling on the central system. You have material that's flowing on from random directions. And at the same time, it's a little hard to see, but you see these blowouts of material. Those are the stars forming, dying, going supernova, and ejecting material outside of the galaxy. And so at early times, the galaxy is growing in a chaotic atmosphere. It is forming that disk, and that disk is being destroyed on very quick timescales. Okay, and it's really not till the later stages where the universe becomes hospitable to both the formation and the survival of the disk that you form this really nice spiral structure that mimics the galaxy population as we see it. So our simulations are telling us that the formation of the disks we see today occurs late in the universe. Okay? This challenges that cartoon I presented where the disk formed early, acquiring angular momentum from the tidal torques just forms at the center from this gentle cooling, and then that disk would survive to the present day. And then again, here's our friend. So I hope I've well motivated this question. When did our Milky Way get its disk? The answer to this question discriminates these two scenarios. If galaxies form in a smooth and orderly manner where material is simply cooling like the onions of a layer down into the center of the dark matter halo, the disk is forming nicely, then we should find a large population of disk galaxies early in the universe. If galaxies form in the way that our simulations are suggesting, and that disk is being destroyed and disrupted by the continuous bombardment of material on very rapid timescales, then we may expect to not find a large population of disks in the early universe. I am going to attempt to answer this question using 3 independent lines of evidence, which are all telling us the same story. Before I get into that, how am I doing on time? I tend to ramble.
You're good.
Okay,
You're
great.
good.
Okay, before I get into that, I want to perhaps remind you, perhaps introduce you to for the first time, how we study galaxy evolution. This is the Hubble Extreme Deep Field. This is the Hubble Space Telescope staring over a cumulative time of about 3 weeks, I think, at a single region of the sky. And what popped out is this beautiful image. Almost everything we see here is a galaxy, not necessarily like our Milky Way, but it is a galaxy, large galaxy that contains billions to trillions of stars. The very cool thing about this image is that it is also a time machine because light has a finite speed. It travels with a certain speed. So galaxies that are further away from us, we are receiving their light that was emitted at an earlier age in the universe. How we see them is as they were at an earlier stage. So we can use this fact. I could select nearby galaxies. We are seeing these galaxies as they are near the present day. The distance between us and that galaxy is not very large. It doesn't take light it takes light a short amount of time to reach us. Or I could select these more distant galaxies. We are seeing these galaxies as they were at an earlier stage in the universe. And so the name of the game here, and the production value on this talk is about to ramp up to 1 million. You're going to be very impressed with my keynote skills. We sort these galaxies by their distance from us, and it gives us a movie of the growth of these systems. Of course, we are not watching the growth of an individual galaxy, but instead we are watching, if we can match these correctly in time, we are watching kind of like a pseudo movie of these galaxies growing up. So we can keep doing this. Here I've marked, in terms of billions of years ago, the how we are observing these systems. And we could keep rewinding the clock. Just keep adding galaxies at larger and larger distances. And we're now seeing the Milky Way. These galaxies are selected to have the mass that we think the Milky Way had at the time of observation. So if at face value, this is a movie of how the Milky Way may have looked at these times. And this was the limit at the time the study was done that the Hubble Space Telescope can reach, about 11 billion years ago. And so what do we see? Well, we see the spiral structure that today's Milky Way population has really was not there. I don't know. They're very fuzzy, right? They're small. That's all you can really say, right? They're small and they're not spiral galaxies. To really address our question, we need to measure their physical properties. We need more than the imaging. Okay? So the first physical property we want to measure is to measure the kinematic motions of these galaxies. Okay, so we're looking for those telltale signs of disks, those high rotational motions, low disordered motions. And so I'm going to show you some work where we did that. We utilized the Keck telescope to measure the kinematics of Milky Way-like populations at different periods in cosmic time. Let me just introduce the measurement I'm about to show you with a visual. So this is again our simulation. These are late times, early times. We would say that these frames of the movie have small, what we call velocity dispersion. Okay? These are the disordered motions. Okay? So the ordered motions are very high, it's regularly rotating. The velocity dispersion is very low. You can compare that with these early times where the velocities are more random. Okay? We would say that these have large velocity dispersions when the galaxy was kind of growing in chaos. And I feel like this is the perfect crowd to show you exactly what we're measuring. So what we do is we take a galaxy and we take a slit along the galaxy. That slit lets light pass through and it blocks all other light. So it's something like this. That light that passes through the slit is then passed to a diffraction grating, and the light is spread out in wavelength. And so what we end up with is what we call a 2D spectrum, where this direction is the position along the galaxy, and this direction is wavelength, with red to the right, blue to the left. We could convert that wavelength into a velocity because the wavelength and the velocity are related by the Doppler shift. This specifically is the H alpha line, which you may be familiar with. This is a transition line of the hydrogen atom. And so what are we seeing here? Well, we are seeing that this portion of the galaxy has a velocity of about negative 150 kilometers per second. It is moving relative to us, relative to its center, at about 150 kilometers per second. Whereas this side of the galaxy is moving away from us at about 150 kilometers per second. What we are measuring with the tilt of this line is the rotation of the system. One side's moving away, one side's moving towards us. This is the telltale sign of rotation. The width of the line at a given position tells us the disordered motion. So if I fix my position in the galaxy, You have some hydrogen atoms moving that way, some moving this way. They are creating this width. If they're moving that way with a large speed and this way with a large speed, and the turbulence is very high, this width would be much larger. So those are how we make our two measurements of interest. And so we could compare that galaxy I just showed you with this one up here. And you'll notice that the width of the line at a given position, this width here, is comparable with that tilt, right? So we would say that this system has high disordered motions, low rotational motions, and this system has high rotational motions, low disordered motions. So this is how we make the measurement. And I'll just jump to the punchline. Before I show you any results, we'll just introduce the plot. The y-axis is the velocity dispersion. Those are those disordered motions. The x-axis is the age of the universe going backwards. So the present day is the left-hand side. 12 billion years ago is the right-hand side. Just to reframe this measurement in terms of our visuals, we have regular disk rotation on the bottom here and disordered motions on the top. What we find, and I'm a very theatric person, so I'm going to reveal this a little at a time, is that the galaxies closer to the present day have disordered motions of about 20 kilometers per second. I'm splitting these between high mass galaxies and low mass galaxies. If we push back a little further, what we find is that the velocity dispersion is slightly higher, maybe 40 kilometers per second. And if we push back to the furthest that our observations allow us to reach, we find that the velocity dispersion is extremely high, 60 kilometers per second. So the velocity dispersion, these disordered motions, decrease by a factor of 3 from the early universe, from this period, to the present day. Okay. The really interesting thing is that this number, 60 kilometers per second, is about 6 times the sound speed of this gas. What that means is that you cannot have hydrogen gas with a velocity dispersion of 60 kilometers per second not collide and decay. Okay, so the fact that most of the population has these high turbulent motions means that energy is being fed in at a rate that is quicker than the rate that it would naturally decline. Where does that energy come from? From the supernova explosions, from the material falling onto it. So these galaxies are very much unlike disk galaxies in the present day, which have these low disordered motions. They're much more turbulent. So that's one indication that perhaps this more chaotic view is the correct view. This got us thinking about another measurement that folks who study local disk galaxies really love, which is called the age velocity dispersion relation. If you take a disk galaxy like this, we're looking at it at John, and you ask the question, where do the youngest stars live in this galaxy? They typically live close to the midplane. That's because this is where all the gas is. The stars form and they hang out in the midplane. And then you go up and you ask, where do the next oldest stars live? They also lie in the midplane, but they also tend to lie out of the plane. And if you ask the question, where do the oldest stars live? Those tend to lie in the midplane and the outer plane, but also at very large distances above the plane. So there's a relationship between the age of the star today and its location in the galaxy. So how was this interpreted in our classic understanding of disk galaxy formation? Well, remember that classic story is that thin gas disks form early on, and then presumably stars start forming out of that disk. Okay. So stars are forming out of that thin disk, and then as time passes, those stars will collide with asymmetries in the disk and be kicked to higher distances above and below the midplane. While that's happening, a new generation of stars is forming. So then we replace that older generation with this newer generation. Let's go one more time step. That earliest generation thickens more. The second generation also thickens, and then we replace it. And so you get this structure where the youngest stars are in the center. The oldest stars, which have been circling around the galaxy for longer periods of time, have been kicked above and below the midplane. This was the classic explanation here. But I want to pose to you another explanation, which is perhaps at early times, when the gas is extremely turbulent, the stars are forming in a thicker disk. They don't form in a thin disk, they form in a thicker disk. And with time, as the gas dispersion declines, stars are formed in thinner and thinner disks. Okay? So we get the next generation is formed in a thinner disk, and the final generation is formed in this thin disk. Okay. What I want you to notice is that the present day, both of these models, which are wholly inconsistent with each other, produce the same result. You can only discriminate which one is correct in the early universe. The question is, were stars in a thin disk at early times, supporting the left hypothesis, or were they in a thick disk? And so we just decided to go out and make this measurement using the Hubble Space Telescope. This is work done by an excellent student, Kathleen Hamilton Campos. The idea here was we selected galaxies which we think were the most edge on at their given time. And then from these galaxies, again, I think this is the perfect audience to really tie into the measurement here. We get a profile like this. This is the galaxy. We're looking at it edge on. The Hubble Space Telescope, it's an amazing telescope, has really nice spatial resolution, but of course there will be a point spread function. Okay. So there's some natural spatial resolution that the Hubble Space Telescope has. And it turns out that these galaxies are so thin that it competes with this point spread function. So what we are looking for is broadening, thickening beyond the point spread function. So this is what we're left with. We're looking at this profile. This is the expectation for an infinitely thin disk. What you'll notice is that there's a little bit of thickness here. That is our measurement. This black portion tells us the thickness above and beyond what you expect from the point spread function. So we made these measurements for hundreds of systems. And I'll introduce our plot again. The x-axis here is the thickness of the disk, which we refer to as the scale height. Here is the young, thin disk in the Milky Way today. Here is the older, thicker population. And to remind us of our expectation, the classic galaxy formation theory says that this older, thick disk has not had the time to form early in the universe. So we should expect, if we were to make this measurement at early times, that all the galaxies pile up here. But it turns out what Kathleen found was that the galaxies are as thick at early times as the thick disk is today. That is to say that the thick disk was already formed at early times, supporting that second hypothesis. Still doing well on time? Okay, the third measurement. We have two measurements now that are both hinting at this more chaotic formation scenario. The velocity dispersions are very high and the galaxies are thick. Their stars are thick. The third measurement is attacking that question about the distribution of metals. As a reminder, here's our periodic table. We're very lazy as astronomers, the collection of us. I'm going to lump everyone in this room into that lazy category. And so we say that, okay, this is too much information. It's giving me a headache. We're going to reduce this to hydrogen, helium, and the rest of the periodic table we're going to call metals. And we're never going to talk to our chemistry friends because they would probably throw something at us. But these heavy elements are distinct from hydrogen and helium because they are formed after the Big Bang. Hydrogen and helium are created in the Big Bang. The heavy elements are formed later in stars, in the cores of stars, and released when those stars either explode or through their winds. Okay? So they are a distinct population. And I want to pose to you the following thing. Imagine we have stars forming in our galaxy. Okay? And if I plot how many stars there are per volume as a function of the distance from the center, it falls off something like this, where you have a lot of stars per volume in the center and fewer in the outskirts. If those stars form, explode, and deposit their metals locally, that is that the gas is not allowed to leave the birthplace of the star, then you would expect that the heavy elements would follow this exact trend. That they too would be distributed more so in their centers than in their outskirts. This is exactly what we find for the local population rate. But let me again come back to our simulation and take a look at what it's telling us. The right-hand side now is that metallicity. What it's telling us is that that proposition I just stated is completely incorrect. That in fact, gas is flowing all over the place during these mergers, during these blowouts, and the metals follow along. They're deposited outside the galaxy, they come around. I've heard an estimate that the metals that make up the Earth, this table, have cycled, I don't want to get the wrong number, I think it was at least twice into and out of our galaxy before converging to form the Earth. And it's only at like times where you form this dense core in the center. So we decided to go out and make this measurement with the Hubble Space Telescope. I won't get into the data, but what we get out are these maps of emission. These are 2D maps now. This is of hydrogen. We also get them for the oxygen atoms. We can take the ratio of the oxygen to the hydrogen and get at the metallicity, the relative ratio of heavy elements to hydrogen. So these are what the maps look like. Scoop up this. Get to the punchline. The y-axis of this plot is a measure of that distribution, the gradient of the metallicity. Okay, we expect galaxies down here if they stay put after birth. That is, they're more centrally concentrated, and we expect them here if they're spread all over the place. They would have no gradient. Okay, so these are our expectations. When we look in the early universe, we find that most of the population is up here, consistent with this picture of metals blowing out and being redistributed. And presumably, the redistribution of these metals is following the redistribution of the gas. So this is now the third line of evidence that indicates that galaxy formation is just extremely messy in the early universe. Okay, so specifically 10 billion years ago, we find that random motions are providing most of the dynamical support, and that the heavy elements in the gas are being redistributed on very rapid timescales. And so this indicates that the Milky Way forms its disk late in time, challenging that classic picture that we've come to know. Okay, I have just 2 more slides. I won't bore you with the rest.
Can I ask a question?
Sure, yeah, absolutely.
You haven't talked about the implications of dark matter and that impact on this model.
Yeah, so the role of the dark matter is to effectively bind all of the mass together. It's to give it a central point. The dark matter otherwise is relatively inert in this picture. That is that it hangs out in this giant sphere. We call it a dark matter halo. This is the modern picture. We have no observations of this, but if we adopt this picture, we produce observations of the normal matter that reflect our reality. But the idea here is that the dark matter hangs out in this halo, and it can't bleed off energy, can't collide, and so its role is to just simply provide a resting place for the normal matter.
So eventually the spoke-like motion takes over then, where, I shouldn't say spokes, but.
For the dark matter?
For the stars moving about the galaxy at the same speed in the rim as they do on the interior.
Do you mean, so when you say spoke, do you mean that it's a uniform,
yes,
that everything is, yeah, so that is not the picture. That picture would produce a rotation curve that is inconsistent with one that we find. Yeah. Okay. Those are excellent questions. So this is a really exciting time for this field because there are what I think of as 3 new frontiers for extragalactic science. One, we are beginning to make these simulations with increasing realism, with more powerful supercomputers, with more well-justified physics underpinning the simulations. We're able to just now start making measurements of the cold gas in these galaxies, not just the hot ionized gas. And really, the James Webb Space Telescope is the most interesting. We're going to skip over all of these. Okay? We're going to skip them. You can enjoy them. They're beautiful. Okay, the James Webb Space Telescope. Okay, this is the most powerful telescope that humanity has ever built. And there are 3 reasons that make it so powerful. The one is that it has near and mid-infrared sensitivity. So if we want to observe those galaxies in the very early universe, their light, by the time it reaches us, has been redshifted, which means that it's pushed to longer and longer wavelengths. Okay, so we need to go into the near and mid-infrared to observe this light. It has a larger mirror than Hubble, so it's just a 7 times collecting area bucket than what Hubble could give us. That's a number of very sophisticated instruments on it. It launched in 2021 on Christmas morning. Did anyone wake up to see it? It was 7 a.m. Eastern. It's beautiful, beautiful Christmas gift. Here's the launch. And it started immediately producing really incredible images. This was one of the first images that came out of the observatory. And this quote always stuck with me. This was the project scientist for JWST. She said, wherever we look, it's a deep field. Remember that extreme deep field I showed you that Hubble stared for 3 weeks? You do not need 3 weeks to produce an image as striking and at the level of depth of that image with JWST. I forgot, I think this was, I don't want to start spreading misinformation. It was less than 5 hours. I don't remember the exact time of that this image was taken. And you get so, very crisp detail. You're seeing a lot of red light that the Hubble Space Telescope was not sensitive to. So it's just a beautiful observatory. It's giving us this amazing view. I've been working most closely with this program. This was the first extragalactic program taken by JWST. It's called SEERS. The graphics team at NASA produced this striking movie where if we have the distances to these galaxies, we can use a computer model to act like we're flying through them. So we're flying through. Of course, JWST is not producing a movie like this, but this is using the information we get. Okay, skipping that. Because I'm going to tell you that this is a very exciting time, not just for extragalactic science, but extragalactic science in Rhode Island. So one of the questions we're really interested in, this is that curve I showed you, the velocity dispersion increasing, is what does this do in the very early periods of the universe? The first 2 billion years that the Keck Observatory and Hubble were effectively blind to. Okay? Does it drop down or does it continue to rise? And there are expectations that or there are reasons to expect either of these. Another question we have is, what are the properties of those blowouts? How fast is material being ejected from these systems? How many metals are they carrying along with it? This is a measurement that only JWST can really make. And so in March to May next year of 2026, we have this approved program for 65 hours where we're going to go out and target this early population with a spectrograph on the James Webb Space Telescope. This is going to be led out of Providence College, but it's an international kind of collaboration with over 10 institutions. And we're going to be getting high resolution spectroscopy, like I showed you before, of the H alpha line, where we measured the rotation curve for these systems for the first time in the very early universe. And again, this is only 8 months away, so there's more to come out of your local community. So I'm going to be quiet there and just present my summary. I think that this is a very remarkable time for extragalactic science. We've now learned that galaxy formation is an extremely messy process in the early universe, but the physics involved with that mess is still a mystery. But over the next decade, with advances in supercomputing and more detailed observations from JWST, we're going to start answering these questions in better detail. I really appreciate your attention and for welcoming me into your community. Thanks, Ted.
You know what? My brain is full. Questions? Oh, microphone.
1, 2, 3. 2, 3.
I can speak loud. Can you go back to the slide that had the linear slit for the spectroscopy?
Yes.
Because I have a question on that.
Sure.
If you go on the assumption that the universe is either expanding or it's static, when you look at that slit and you compare it, you say that the top is receding and the bottom is approaching, but that's a matter of perspective.
Yes.
Okay, because if you reverse that 90 degrees, then it's one side is moving backwards and the other side is moving towards you.
So I'll give you the first point of your question is absolutely correct. It's a matter of perspective in the sense that this entire galaxy is receding from us because the universe is expanding. So I put 0 here with respect to the center of the galaxy, but the entire thing is receding. Yeah, the entire thing is receding from us, and we're measuring these velocities with respect to the center.
Okay. What is the driving mechanism in the very, very beginning when everything coalesces? It can't be gravity because, well, maybe it can be gravity.
It is gravity.
But gravity of what? I mean,
the gravity of the matter. So the matter is the mass, both the dark mass and the normal mass, but mostly the dark mass forms these strings. This is called the cosmic web. It collapses like a string. And then along that string, beads form. You have local collapse, and inside those beads is where the galaxies form.
Well, there's some theory that there's a black hole or multiple black holes at the center of many galaxies.
Yes. Yeah.
Does that add to the rotation and the coalescence?
That's a great question. The black hole, even in the most supermassive black holes that we've measured, are minuscule compared to the mass of the dark matter halo. So the dark matter halo is the thing that sets the majority of the gravity. And only when you get really close to that black hole does the mass of the black hole become important, even for the most supermassive black holes. Yeah.
Laura was next.
My question is about the mass ejection.
Yeah.
Explosion star. Is there any? Are there any measurements or impacts of whether that mass is totally escaping the gravitational field of the galaxy, or is some of it recaptured, and what's the impact of that?
That is a terrific question because that is one of the gold standard observations that we're after. And it's one of the questions that we're going to go after with our JWST program. Where we can make this measurement, it's difficult because you can make a measurement of the velocity of the gas, but the question on the local, we call this the escape velocity. It's how much velocity you need to completely unbind yourself from the system. That escape velocity is set by the dark matter, which we can't see. So we have to model what that escape velocity is. And to our best assumptions, the gas is right on the cusp. So it's if the escape velocity is 500 kilometers per second, the gas is typically ejected with like 300 to 700. So some of it will be recaptured, some of it will escape, and that depends on the galaxy type and other things. But that's the key comparison to make, yeah, when you're asking about this recycling.
Either observational or the other about the eventual fate or spiral galaxy to speed up, wind down, and fall apart?
Yeah, that's a great question. So long as there are no major collisions, which we are expected to have a collision with Andromeda, if there were no major collisions, the gas would gradually be consumed. There would be no more gas. You would only have stars. Those stars do not collide because there's too much space in between them. They don't really interact gravitationally either. And you would just have this spinning top of stars for all of eternity. But we are set to collide with Andromeda in about 5 billion years. And the result of that collision may be a sudden pop in star formation. As the gas coalesces and it gets really dense, stars will form rapidly out of that. So you get a rapid consumption of gas. And depending on the specific nature of that collision, the result may be a spherical shape or it may be a disc shape. And I don't think that that's well determined.
I'm still struggling to understand the role of dark matter and its implications in all this. In the absence of any interaction other than gravity, you would expect dark matter to also be coalescing as the rest of this goes on. So something must prevent that.
Yes, you expect a small coalescence, but the idea here is that the dark matter cannot get rid of its energy. So it has orbital energy associated with its motion. The gas, you imagine you have a gas particle moving like this and a gas particle moving like this. That gas is very dense and will self-interact, and that orbital motion will leave the system. It'll be radiated away, and so that gas will fall into the plane. The same thing doesn't happen with the dark matter. They effectively pass by each other, and so you can't get rid of this energy, so it just remains in this halo shape.
So, does your initial distribution of dark matter as you set up the simulation, does that influence any of these outcomes?
It does. Yeah, it does. It is very. There are a few things that are well constrained by other measurements, and that is the relative mass of the dark matter to the normal matter. And so you start off with a box where you populate each cell of the box with a certain fraction of mass of dark matter, a certain fraction of normal matter, and you just let gravity do its thing, and it will form these spindles that I was mentioning. And then in those spindles, you'll get this local collapse. And that's really where our simulation kicks in, because then we say, we're going to start off with this picture of the structure of the dark matter and normal matter. And we're going to hyper focus on one of these beads on the string and go from there. Now, if you were to change the relative mass of dark matter to normal matter, or you were to change the expansion rate of the universe, the details of those spindles do change. And those could have knock-on effects on the structure of the mass. But the generic conclusions I drew here, that material is just falling in very rapidly, the merger rates are very high. Those are robust to changes in what we call the cosmology, which is
The dark matter distribution and visible matter distribution match until collisions become significant.
Yes. Yep. Yeah. That's the idea. That's the idea. And the collisions become significant pretty quickly. So they disconnect pretty quickly.
Any other questions?
Well, thank you, Raymond.
Thank you, guys.
But Rick, as was indicated by Kathy, is a great storyteller, and really part of their outcome is
one of your boys.
Yes, figures very large in the development of amateur astronomy in New England, particularly with regard to variable stars. He was a pioneer in helping forming the AAVSO, but I don't want to get into telling the story. So without further ado, please help us give a warm skyscraper hello to Rick Lynch. Thank you.
No, you'd be surprised how loud I can be.
You can build up.
Okay, thank you, everyone. I want to remind everybody that we're very fortunate living in the Northeast because, quite frankly, when this country was founded, astronomy came from Europe and it landed in New England. And there were many, many, many famous people that were involved in astronomy, and a lot of them were amateur astronomers. And there was a very fuzzy line between amateur astronomy and professional astronomy in the late 1700s and the early 1800s. And people like E. Barnard, who was actually from Vermont, Todd, it just goes on and on and on. Trouvelot, the famous artist of deep sky objects and everything else. And those people was a man by the name of William Tyler Olcott. And I'd like to tell you a little bit about the history of William, but I'd also like to give you a little some side stories that are kind of attached to him and actually to the observatory here, to Frank Seagrave. But this is the life and times of Willie Tyler Olcott. He was born on January 11th in 1873 in Chicago, Illinois. He was born to a family that was fairly well-to-do. Okay, I wouldn't say they were rich, but they were comfortable, and you could tell from when you look at his education. He was the son of William Marvin and Olivia Tyler Olcott, And he moved to Norwich, Connecticut at a young age. Tyler Residence was built in 1768 by Reverend John Tyler, who was the first rector of the Christ Episcopal Church. The church still exists today on the hilltop in Norwich, across from the homestead. And the homestead stayed in the Olcott family for quite some time. He attended local schools and graduated from Norwich Free Academy.
Yeah.
Now, you know Norwich Free Academy. It's a very unique academy in that it actually has an archaeology and art museum on the scale that a university would have. And this was a high school, okay? And it was a rather large complex. He got his BS from Trinity College in Hartford, Connecticut. And Trinity College, for those of you who know Hartford, know Connecticut, is pretty much in the center of the city for all intents and purposes. But in 1896, you're going to see pictures of what Hartford looked like. And he graduated from Columbia Law School with a degree in law in 1900. And he went back and he got his MA from Trinity College in 1912. Now, this is a very early art piece of Norwich Academy, and it was founded in 1854, and this was the original building. It was called the Chelsea Parade, and it began classes in 1856. So this is the building. Now, the building is now a campus, but if you look closely at the building, in the next slide, you'll see the building without the spire on the top, okay? And you can see how it's expanded. And what we have over here is this is the museum. And of course, this classroom, this is the Museum of Art and Archaeology, Anthropology in there. It's a rather large complex. But in some ways, you went here and it was pretty much like a prep school, but it was built for the benefit of everybody in the public, those who could afford to go and those who couldn't afford to go. But the quality of the education there was exceptional. In 1982, I visited it because I want to take pictures of when I was researching Olcott, and I realized that they had an observatory on the top, and it had an ash dome on it, or an observer dome, an aluminum dome, and you can see it was prominently located on top. I don't know what was in there for an instrument, but what happened was I went back again, and I went there in 2025, and if you take a look here now, okay, you can see it has a fiberglass observer dome on it, okay? I don't know what transpired from before to now. And based on the antennas and the way it's set up, it's not being used much. Ironically, I went inside the building and I asked them if there was anybody I could talk to or if they had any history on the observatory on the top of the roof. And she goes, observatory? What's an observatory? I said, well, the telescope is. And says, oh, I don't know if we have a telescope here. I says, well, you have a dome on the roof with an observatory on it. And she goes, I've never seen it. And I've worked here all this time. And I said, well, boy, I guess astronomy isn't as prominent as it used to be. But if you look at the antennas, you know it's not being used. So that's a little diversion there. But he went on to Trinity College, okay? And this is Trinity College, an original postcard taken in 1907. And this is in downtown Hartford for all intents and purposes, okay? It's a big place and it's a liberal arts college, but it's a pretty prestigious college. And I think you can get a law degree here also. I'm not sure, anybody know any alumni from Trinity College know anything about the curriculum there?
Tucker Carlson.
Dr. Carlson came?
Oh, thanks for that.
Okay, this is 1907, and this is a painting, well, not a painting, it's a pen and ink of Trinity College in the center of Hartford. So take a look at it. And if you look at this little arrow here, I put this arrow in here, and there's a little white dot there. Well, Olcott came to Trinity, and the next slide will tell you. Olcott came to Trinity in 1883. This is the observatory that arrow pointed to, and this is St. John's Observatory. It was built in 1895 for the Venus transit marker. And the Venus transit marker is right here. If you went to the campus now, you could actually find that. Okay, the 1882 transit of Venus. And I was able to find out that there was a 6-inch Fitz refractor in it. And I said, that's pretty interesting. And then I did a little bit more digging around and I found another photo. And once again, this is downtown Hartford. Skies were pretty good back then. This is what the observatory looked like in 1895. And it had a 6 5/8 brashier refractor on a Warren Swayze mount. Well, you know, I'm looking at this and Olcott never actually observed through this because he came a year after it. His spark in astronomy hadn't been ignited yet. But I said, I wonder where those telescopes are. So when you think about old telescopes, the first thing you think about is the Antique Telescope Society. Wonderful resource. There are people here who are members and they can give you a wealth of information. But more explicitly, you think of John Briggs, who's a member of Skyscrapers, used to live in the area and is now in Magdalena, New Mexico. And I called up John and I says, John, you know, I'm giving a talk on Olcott, and part of it is I'm talking about Trinity College and when he went there and everything. And he goes, oh, yeah. I said, listen, I know he had a 6-inch Fitz, and then later on they put a 6 5/8 brashier refractor in there. And I said, I think it was given by a wealthy benefactor, alumnus of the university named Dr. St. John. His name was St. John. And he says, do you know anything about the telescopes or where they might be? He goes, yeah, I got them. And I said, really? And he says, you probably have seen them. I said, oh, really? Well, anyway, for those of you who have ever been to Magdalena, New Mexico, this is John Briggs.
Bruce Lee Adams.
Bruce Lee Adams.
He's evolved off the main seat.
He ended up buying the high school building in Magdalena, New Mexico. Now, a number of us have gone out there when we went up for the eclipse, and some of us have been out there before. Steve Hubbard's been out there, has visited John and everything else. John has one of everything. He actually has refractors stacked like cordwood on special racks, tube assemblies and everything else. But he's acquired so much that he just is not that well organized. And he's become a little plump and he can't do the kind of work he used to do and everything else. But everywhere you look in here, there are telescopes. You can see Jim Hendrickson is right here when we visited. And you really can't get an appreciation for this, but there are telescopes everywhere. And the picture goes off to the left. It goes farther back. And he calls this his Lyceum. He took over the auditorium of the high school, and the rest of the high school, okay, he rented or he went partners with a gentleman from Atlanta, Georgia. I can't remember his name. Sky Telescope did an article on him. And he's another guy who collects equipment, but not ancient equipment. He will go when NASA is having something that they're trying to get rid of, he'll go and make bids on it and everything else. When we were there, he introduced us, so he took us on a tour. There was like 6 domes in the back. They had satellite tracking stations that he had picked up for like $1,600 or for the price of scrap metal. He said, oh, you see that camera there? There was a camera there with a lens like this big. He says, this came off the SR-71 Blackbird. This was used for imaging and everything else. So there's a lot of astronomy going here. But Magdalena, for those who've ever been to New Mexico, is not the hub of the universe. It's on the way out to the VLA, but this is his place. He gave me a rundown on everything, and he was a pretty good resource of information on some of the things that I was interested that were related to this talk in Olcott. Well, William graduated from Columbia Law School in 1900, and he was not into astronomy yet, okay? They were living in their home, they were living in the family home in Norwich, Connecticut. And 2 years later, and some of this stuff came from his family collection. Some came from the AAVSO, some of the images, some of the stuff that I've imaged. He got married to Clara Eunice and William Tyler Olcott on Monday, the 16th of June, 1902 in Yantic, Connecticut. Okay, Yantic is a town within Norwich, Connecticut. He was a dapper guy, but this was at a time when everybody who was any kind of an astronomer, amateur or professional, always wore a three-piece suit, wore a top hat when they weren't observing and everything else. You had to dress formally to observe, no matter what the temperature was or anything else. He gets married. Once again, family's fairly well-to-do. They're living in Norwich, Connecticut, up on the hill, okay? But they also have a summer home, and I'll tell you about the summer home. This is the glebe house. This is the house that he lived in, and you can see it was built by Reverend Tyler, and directly across the street is the church. Okay, if you look at the house very closely, you'll see that in 2025, the house is virtually the same. Okay, it's exactly the same. Okay, and there is a little historical plaque on the door. Now it's built on a very steep hill, so the backyard's has got a steep hill to it. Okay, and you know, I'm walking up the street and I'm walking a little parking area behind it. I'm taking pictures, and some people came out and they said, "Hey, what are you doing?" And they thought I was like real estate or something. I guess what they do is they rent it out now. There's 2 apartments or something in there. They rent it out, and I go, "Well, I'm just taking some pictures. This was the home of a very famous person." And I go, "Oh yeah, who was he?" And I said, his name was William Tyler Olcott. "Oh, I never heard of him." I said, "He was a famous astronomer." "Oh, he's an astrologer. Did he do a lot of fortune telling and stuff?" I go, "He was an astronomer." He goes, "Oh, okay. Well, I didn't know that. Go ahead, take your pictures." I go, "Thank you." Okay. Anyway, while he's living there, they have every summer they would go somewhere, either to Block Island where they had a home. Okay, they had a summer home in Block Island, but they would go to a lot of other places. Later on in his life, he moved around to other places. He went to the Southwest quite a bit, and we'll see that a little bit later. He went to Florida, to Miami, New Hampshire. He went to a lot of places, but this is their home on Block Island, on the bluff. And this was a party that Mrs. Olcott threw, and the prize was a basket of candy. Was won by Miss Mabel Webb, and this is dated August 29, 1903. While he's on the island, okay, you got a lot of spare time. You take it easy all during the day, and one thing that really caught his attention, at night the sky is exceptional. So this is the Milky Way from Block Island looking towards Point Judith, okay, and you saw earlier in one of the talks the Milky Way. This Norwich was pretty dark, okay, but he had never really noticed the sky, and this made a big impact on him. He became very interested in astronomy, and it was after this that he decided he wanted to share that with the public and more people so they would appreciate it. He was concerned that people living in the cities where they had all the coal smoke and everything else like we had in Providence when Seagrave moved here, that they would never get to appreciate the night sky. And he thought the best way to do that would be to put together some kind of guidebook that would be beneficial. But he had to learn a little bit more about astronomy first. Whoops. Okay. I asked John about this. He had acquired a telescope, okay, and this is taken in the backyard at the glebe house. You can see the fence, which is still there, not quite the same fence, but it's a steep inclined backyard. And John thought that this was a French telescope, and it was probably 4 or 5 inches, and it was a portable. We don't know what happened to this telescope. And the other thing is, it didn't come from the AAVSO loaner program, which we'll talk about momentarily. But seeing that Milky Way, seeing that night sky, being very interested in astronomy, he really pursued it with a passion. He was a well-educated man, and he didn't need to work as a lawyer, but he did need to, he needed to, when he got involved in something, he really jumped into it. So he came back and he says, "I'm going to build an observatory." And if you look, this is his observatory, okay? And what it is it's a 6-sided pyramid, and it rotates on the top and everything else. And he built it right on top of the house, and you can see the church directly across the street, which wasn't a problem. This is the house today, and you can see the church, and this is where the observatory originally stood. If you look back, you see the chimney. There's one here. There's one right behind it. There's one in front of it. So this is where the observatory was. I didn't want to get into detail with the people that were there. They were clueless. So, but I wanted to document that. Well, this is what the observatory looked like. This is a little bit later on. This is a famous photo. And if you take a close look at this, and there's some controversy here when we talk about this telescope and where it eventually ended up. If you take a look at the size of an ordinary human head, and you look at these pictures, which are actually 11 by 14 frames with 8 by 10, a little bit more than 8 by 10 images in there. This is Comet Biela. He had decorated the inside of the dome, and it also had an electric pier which would rise up and down. But if you take a look at this tube assembly, okay, in this picture, it looks bigger than a 4-inch. I have a 4-inch Mogi, which used to be here, which I bought from the club, and it's just a lot smaller than what this appears. But all the records say that his telescope was a 4-inch Alvin clock, and I can show you the documentation for it. But this is him. He's already now become pretty well engrossed in astronomy. But his first book he writes is A Field Book of the Stars by William Tyler Olcott. Many readers of this book may be fortunate possessors of small telescopes. It may be that they have observed the heavens from time to time in a desultory way and have no notion that valuable and practical scientific research work can be accomplished with a small glass. If those who are willing to aid in the great work of astrophysical research will communicate with the author, this is written on the inside of the book, okay, the most practical and fascinating line of observational work which will enable them to share in the advance of our knowledge respecting the stars. It is the work that involves no mathematics, and its details are easily mastered. Well, he put this in his book. This was his first book, okay? And it was a call to anybody who was interested in doing something. Well, what was that valuable research he was talking about? Well, that valuable research was variable stars. The immortal astronomer Arglander was the first to actively engage in this branch of research work. During his sojourn at the observatory at Bonn, Germany, he made up a map of the sky which included more than 600,000 stars down to 9.5 magnitude. That's the Bonn Deutschmusterung catalog, which was the most famous catalog of the time, and he eventually had it extended into the southern hemisphere and everything else. As a deciduous observer of long-period variable stars, he expressed the hope that someday others would follow in his footsteps and record their observation of these enigmatic stars. This is the Bonn Observatory, kind of in some way similar to what Olcott had built. Not dome, but it did rotate. And this is Arglander. Well, the Harvard College Observatory, famous for its research work in stellar photometry, took an active interest in the observation of variable stars. Mr. Leon Campbell of the Harvard College Observatory staff carried on these observations for many years, and a few observers, notably Frank E. Seagrave, Professor Annie S. Cannon, Miss Helen M. Schwartz, Carolyn M. Furness, and a few others contributed their observations to the observatory. It was always the hope of the director, Pickering, that someday an association of amateur astronomers would cooperate in this work. In the September 1911 issue of Popular Astronomy, the editor included in his notes this query: can we have an association of observers with a variable star section, a Jupiter section, etc.? Popular Astronomy, for those who you don't know, and we have a fairly good collection downstairs in the observatory, was the Scion telescope of the turn of the century. It was put out by Carleton College in Minnesota. It was almost a book in size. It came out every month And it was the place, if you were a professional and if you're a well-to-do amateur astronomer, this is what you would subscribe to. The writer began the active observation, Olcott began his active observation of variable stars on February 2nd, 1910, when he succeeded after a long search in locating the field Omicron Ceti. The article in Popular Astronomy relating to the formation of variable star association appealed to him as eminently desirable, and he offered his services to organize such an association and to edit monthly reports. My batteries are going dead. Okay. While he's doing this, Olcott becomes a prolific writer. These are 3 more of the books he wrote. Actually, 4 more of the books he wrote. They're all collector's items. Now, Lloyd Merrill isn't in here, is he? Lloyd Merrill, when he saw the first advertisement that we put out for this year's AstroAssembly, he saw the list of speakers, and he saw that I was speaking on Olcott, and he had called. When he came to the meeting a couple of months ago, he came up to me and he says, "Hey, I got to show you something." And I go, "Yeah, what's that?" He says, "You're talking on Olcott." I go, "Yeah." He says, "You're going to talk about his telescope?" I says, "I'm going to talk about as much as I can tell you about his telescope." And he says, "Oh yeah, I got to show you what I got." He showed me 2 books, okay, and they were handwritten. I mean, they were signed by William Tyler Olcott, and they had Olcott's what do you call the page you put in a book when you
A book plate.
a book plate? And he says, "I picked these up on eBay." I says, "How much you pay for them?" And he says, "I don't know, $20 for both of them." He goes, "Yeah." He says, "I'll give you 100. He says, "No, I'm going to hold on to them." Then he showed another one by Hale, okay, on the 200-inch, and that was signed and everything else. And I says, "How much you pay for this one?" He said, "I don't know. This one was only $6 or $7." I said, "Oh boy." I said, "If you want something, let me know." Anyway, he writes the books. He's really popularizing astronomy. His passion now is in variable stars. He's learned to observe variable stars. He's communicating regularly with Harvard College Observatory. Well, the founding of the AAVSO, for those of you who don't know, the AAVSO was the American Association of Variable Star Observers. Early in 1911, Pickering establishes a group of observers. Those are the ones we mentioned before, of which Frank Seagrave was one of them. April 1914, William Tyler Olcott organizes an informal meeting in a restaurant in New York City to become officially known as the AAVSO. November 1917, the first annual meeting is held at Harvard College Observatory. I think Harvard College donated $100 to the founding of the organization to get it off the ground. $100 back then was quite a bit of money. And in October 1918, they officially organized and incorporated as the AAVSO. Now, what happened was the AAVSO, and this is Olcott again writing, the history of an organization that has achieved its aims and won recognition of the scientific world is noteworthy and of interest, particularly so when it is a record of an amateur endeavor. So he's basically saying, look what we've done. We're amateurs and we're contributing immensely to the scientific community and everything else. He became the secretary, the first secretary of the AAVSO, and he was the secretary right until his death. So he was one of the original founding members of the AAVSO. He had a policy that no letter written to him at the AAVSO, or for that matter on any subject of astronomy, he would respond back to each and every letter in 24 hours, which he did. That was his policy. So he was a prolific letter writer. Well, an early observer was a young teenager from West Central Ohio, observing from his family farm. His name was Leslie Peltier. You probably have heard my talk, or you've read Starlight Nights. You know the story of Leslie Peltier. This is the telescope he got. It was a French-built 2-inch that he got from picking strawberries on his father's farm. He saved up the money. He got this telescope, and one of the first books he read, one of the first things that happened in his family was they lived on a rural farm in Ohio, And when Christmas came, one of the best gifts you could give, other than nice warm socks and a jacket or something, was books. And they always gave each other books, and they had a nice little library, and Peltier just read all the time. And one of the books he received was Martha Evans' book, which was the very first book that introduced him to astronomy. He became passionate, and he had started with the help of that book, looking at many things. And then he received, when Christmas came, that first stargazing year of 1908, my mother gave me a small book entitled A Field Book of the Stars by William Tyler Olcott. Just as the Friendly Stars had been, the Friendly Stars was Evans' book. It was precisely the book I needed for it to begin its story right where the first book had stopped. The first one was just a general history, a general overview of astronomy. These are the things you can see. These are the primary craters on the moon. This is when the planets are up. These are the brightest stars. This is double. These are some of the galaxies and diffuse nebula you can look at. But it was after that he wanted to get into something a little bit more serious. And if you remember the story, he wrote to Olcott after having read the book, and he said, "I'd really like to get involved." And he says, "Well, you know, the only requirement really is that you need to have at least a 3-inch telescope, and then you can start observing." Well, he had a 2-inch telescope, but he really wanted to do it. And he says, "Well, listen, I should be able to still look at some variable stars with a 2-inch telescope." So when he wrote back to Olcott and he wrote down the size of his telescope, he smeared the ink so that you couldn't tell if it was a 2 or 3 or a 4. Okay. And Olcott wrote back and says, "Yeah, you're okay," and sent him some hand-drawn charts. And this is one of the hand-drawn charts of Leslie's. This is for RX Tauri, one of the first variable star hand-drawn charts sent to Leslie Peltier. And for those of you who've really been involved with AVSO for a long time, all the charts back then were blueprints. Okay, so this was one of Leslie's charts that was hand drawn from the Harvard plates by Olcott and then blueprinted. The AVSO grows and continues to prosper. Word got out, and variable stars became a real passion for a lot of people. And what ends up happening is the thing starts to grow exponentially. We heard Mark today talk about where we are today as far as the AVSO and smart telescopes, but the history coming through and the amount of observations, all done visually back then, was really, really impressive. And I apologize. Yeah, I think my battery is getting low. Okay, the 11th annual spring meeting of the American Association of Variable Star Observers was held at the Olcott Observatory. It was international in that it probably, I'm gonna exaggerate the numbers because I don't know exactly what the word. They might have had 300 to 500 members worldwide. Domestically, they probably had maybe 200, and locally they probably had, I don't know, 50 or 60. But back in 1922, if you went anywhere of a great distance, you went by train. So when they had their annual meeting, most of the stuff was always held at Harvard College Observatory, but you could have some at your own observatory. And Olcott invited them to have their 11th annual meeting at his observatory. And this is the 1922 spring meeting at the home of William Tyler Olcott in Norwich, Connecticut on June 3rd, 1922. And there are a lot of famous names in here, but we see Olcott here, we see his wife here, we see Leon Campbell here, Pickering, Mrs. Pickering is here. Anyway, this isn't the total attendance, but it's a good majority of the primary people. And they met at his house and he hosted the meeting. One year later, William Tyler Olcott, William Henry, and Leon Campbell, left to right, posed at the AVSO spring meeting in 1923 on Long Island, New York. It was back in these days when no self-respecting observer would look through a telescope without donning a necktie. If you take a look here, take a look at this telescope. I showed John this picture. He felt very strongly that this was a Mogi, okay, and it was a 4-inch, okay. I have a Mogi 4-inch, and the hardware, not the head, but the hardware of the tube assembly, the way the finder is mounted and everything else is exactly the same as what I have. So I would agree that this was a Mogi, but this was just a picture at the next meeting, and they were standing there, and you know they took this picture. But I found this picture because I was happy I got a similar telescope. At that meeting, there were a lot of famous people, and it's not too often that you have like somebody like Dr. Harlow Shapley stay at your house while you're having a meeting and everything else. This is an early Shapley, and this is Olcott. And once again, you didn't go anywhere in those days without a derby hat during the day and your 3-piece suit, and would have you when you observed in your 3-piece suit at night. Olcott became quite famous locally, internationally, and what have you. And this is from the Hartford Courant on December 26, 1920. And it says, Trinity Man, Trinity College, is Secretary of International Body of Volunteer Observers, making valuable contributions to science. And it just tells about his books and his work and the kind of stuff he was doing. And it shows a picture of Cygnus and the Milky Way, and you know, a place for variable stars. Now, if you look, this is taken much later than the original photo, but if you take a look here and you look at the size of this tube assembly, it looks significantly smaller than the original one. Now, everything says that it was a 4-inch Alvin clock, and he definitely owned a 4-inch Alvin clock and used a 4-inch Alvin clock. And I'm sure that this is what it is, but the original looked a little different. I might be wrong, but the William, as he got older, he was still secretary. He was still observing. The cold weather was starting to affect him. As much as he liked to be out every clear night, as he got older, he in the wintertime would have to go to a warmer climate, or in the summertime, they would go to somewhere like New Hampshire for a vacation. William Olcott was never a robust man, and for years he had suffered from bronchial afflictions that necessitated winter sojourns in the South. Other winters were spent in Arizona and California, which brought him in close affiliation with members of the staffs of Lowell and Stewart observatories, as well as those of Mount Wilson and Lick. During his final years, he gave himself rehabilitation of the Southern Cross Astronomical Society. He would go to Miami. He became a member of the Southern Cross Astronomical Society, still in existence, writing and lecturing and aiding in the operating of many telescopes, which the society maintained for the benefit of the public in Miami. So he's down there. He's not like Leslie Peltier. Everywhere he went, he took a telescope and made variable star observations. But when he was in Miami, he stayed active, he lectured, and he certainly helped out at star parties and everything else. This is a picture from his family collection, a friendly squirrel demanding attention, probably at Tucson. If you look up here, there's a squirrel sitting on the top of his hat while he's reading. Okay, and the reason he's in Tucson is he is doing his summertime visits to Stewart Observatory, and this is the original Stewart Observatory and the telescope. There's no Kidd Peak yet. Okay, Kidd Peak hasn't been built. I think Kidd Peak was started in like 54 or 56. So long before that, it was Stewart Observatory, which of course still exists. The skies, of course, were exceptional, and the weather was very conducive to his health issues. He went a little farther north during the summer months, and he visited Lowell Observatory, and he became a friend of Percival Lowell and got to know Percival Lowell. This is the original dome, the 26-inch, and his Lowell sitting at the telescope. Okay, so he was rubbing shoulders with some of the most important people in astronomy at the time. He was technically an amateur astronomer, but from a financial standpoint, he came from a wealthy family, had a law degree. He was better financially than most of the professional astronomers who were making meager salaries, but they were doing it as a labor of love. But he got to visit many of the observatories. He went to Mount Wilson Observatory, and this is Dan Lorraine was docent there, and he ran the 60-inch, and from time to time would show people through the 100-inch. But this is the 60-inch, okay, and this is the 100-inch telescope at Mount Wilson. And Olcott had visited there on several occasions during the summer months. I don't know that he ever observed there. Dan, do they have log books or anything of?
Yeah, they have.
So I'm sure if we worked really hard, we could probably find his name in there. But the place that impressed him the most was Lick Observatory, because Lick Observatory sits on the top of a mountain, Mount Hamilton, overlooking the Los Angeles basin. And you can see it's just like capped on top of a volcanic peak. And the 36-inch refractor was there. And he visited there, and he got to know the people pretty well. Okay. But he also, as I said, would go to the south, go to Florida, and he went to the Southern Cross Astronomical Society. He was actually going to Miami for the winter months, and he found out about the Southern Cross Astronomical Society. And I think they're one of the sponsors of what's the star party that's done in the Keys every year?
Yeah, they actually run it.
Star Party.
Yeah, that's what I thought.
Yeah, they run it. They put it on.
They put it on,
Yeah.
and here we see him helping somebody at a home-built telescope. Skies were exceptional in Miami at the time, as everything was, you know, turn of the at the early 1900s. But when he came back, William Tyler Olcott came back. His health is still not good, but William Tyler Olcott passed away on the evening of July 6, 1936. He and Mrs. Olcott went to George's Mills, New Hampshire on Lake Sunapee for their summer vacation. On the evening of July 6th, he was giving one of his familiar talks on the stars to a group of summer residents in the local Methodist church, which is right here, when his heart attack came and he passed quietly away. Far and wide, his death brought sorrow to hundreds of homes. To those in many lands, this kindly, patient man had been an inspiration and a guide, and this was through his work with the AAVSO as secretary, and of course, because of his books and his correspondence. He was one of those rare souls who loved the stars with an almost religious fervor. His family, his body is returned home to the Antic Cemetery in Norwich, Connecticut, and he's buried in the family plot. This is the family, one of the family stones, and if you look here, it says William Tyler Olcott. So you can go and visit his grave, and it's in Norwich. And a great man passed on, and a lot of people don't realize what an important part of astronomy he was. Certainly the newer people to astronomy don't know about this older history of astronomy, but that's one of the things that I'm kind of passionate about, is bringing this to everybody's attention. The IAU decided that Olcott was important enough that they named the crater on the moon. It's a relatively fresh crater on the far side of the moon. It lies to the south-southeast of the craters Seyfert and Polzanov, and to the north of Kostinsky. Okay, it's actually a bonus crater. This is the primary crater. This is Olcott, Olcott B, A, and I think over here is C. So there's actually 4 craters that are associated with his crater. You can't see it, it's on the far side of the moon, but you can certainly see it in any of the lunar atlases that do the far side of the moon. Telescope postscript. Where did the telescope go? John, you know anything about the telescope? That one he didn't have, but I already knew something and he confirmed it. And with Dennis Chico, I got the necessary information. Some confusion exists about the telescope. William Tyler Olcott passed away in 1936. It would be assumed that his estate would be settled after his death. William Tyler Olcott estate telescope goes to John J. Crane. Okay, John J. Crane estate, when he dies, they donate it to the AAVSO, 1928. Where I'm confused, he passes away in 36. It says, what the literature says, William Tyler Olcott estate telescope goes to John Crane, okay? And Crane goes to the AAVSO in 1928. Well, that can't be, because he's donating it before he's dead, okay? And that didn't happen. But Michael Saladiga and John Briggs gave me some information. Their records show that the AAVSO had that 4-inch telescope, and why there's this discrepancy here, I don't know, but they have records that William Tyler Olcott received it as a loan, okay, and when he died, it eventually came back to the AAVSO. The AAVSO loans the 4-inch telescope to Phoebe Waterman Haas in 1928. Scotty Houston, okay, actually contacts the AAVSO and he gets the telescope as a loaner. And if you read his deep sky columns when Scotty was still alive, okay, he always talked about the view through his 4-inch Alvin clock. Scotty picks up the scope from Mrs. Haas, okay, in 1964. She had stopped observing. It was there. They asked about it. Scotty actually inquired from a historical standpoint, whatever happened to Olcott's telescope? And they said, well, our record says that we loaned it to Phoebe Haas. And he goes, well, is she still alive? And says, yeah, from what we understand. Well, anyway, Scotty made contact, found out that she had the telescope in an ongoing loan. He contacts the AAVSO and asks if he can go and pick it up and they can transfer the loan to him. And they said yes. In 1993, while Scotty was traveling, he died during the trip. Most of you probably know that. The telescope was stolen from his home in Connecticut. And this is a quote from John Briggs. If it ever shows up, it'll be recognized. While Scotty would go down to Mexico quite often when he was going through the Southwest with his little pinata, he called it the little peanut. Many of you may remember his little old trailer. He would go down there and he would spend the winter down there. And while they were down there, he had people that would just go and look at his house. His house was pretty rural. We went down, I don't know, late 80s, early 90s, a bunch of us from Skyscrapers. And I mean, I got slides of that. We went to help him build his observatory. He built an observatory there, and we were down there. So it was a pretty rural dock spot in Haddam, Connecticut, which is along the what do you call it, river?
Connecticut River.
No, the Thames.
Thames? No.
Yeah. Yeah, Haddam is much farther east than the Connecticut.
No.
Up Route 9. Oh no, that's the Connecticut. Anyway, he was in a pretty rural area, but somebody broke into his house and stole the telescopes he had and stole astronomical stuff, but nothing else. So unfortunately, that's a sad reflection on some amateur astronomers or somebody out there who went and did this, and it was really a shame, okay? And people don't realize, at least those people were pretty stupid and didn't realize that if that telescope or that stuff ever shows up with Scotty's name on it, we're gonna know what happened to it.